We can start our section. Dear colleagues, good morning. We continue the section on linear Terahertz photonics, and the first talk will be presented by Dr. Popov, drift current-induced amplification and lasing of TI electromagnetic modes in graphene. Please.
Good morning. Thank you, Mr. Chairman. Can you see my screen?
Yes, we see.
Thank you. So in my talk, I will be talking about drift current-induced amplification and lasing of transverse electromagnetic modes in graphene. This is theoretical work, and it has been done in Kotelnikov Institute in Saratov. The authors of this paper is here. I am Vyacheslav Popov. So let us start. Here is the outline of my talk. First of all, I will give just very brief historical remarks on surface electromagnetic waves. Then I will talk about surface electromagnetic waves guided by two-dimensional layer of material, and especially about transverse electric surface electromagnetic wave in graphene, what is known so far, and then terahertz transverse electric modes in graphene with drift current bias. And then I will talk about hydrodynamic conductivity of graphene with drift current bias and consider amplification and lasing of transverse electric modes in structures with single and double layer graphene. And I will finish with some conclusions. I feel that I have not enough time to go into detail of the history of surface electromagnetic waves, but just for your information, the study of surface electromagnetic waves began since the seminal paper of Sommerfeld in 1899. He considered surface electromagnetic wave guided by metallic lossy wire. And then later, 10 years later, Zenik considered planar surface electromagnetic wave guided by planar surface of lossy metal. In 1910, surface electromagnetic wave guided by dielectric rod was considered, and after that, Hugo Fano considered wave guided by metallic slab having negative permittivity, and now we call these modes plasmon polaritons, but Fano didn't use this term. This term was introduced later by Hopfeld in 1966. And then surface electromagnetic waves guided by slab of dielectric materials and the slab of materials with negative permittivity. This means waveguides with plasmon, phonon, exciton, polariton excitations. And since then, a variety of different surface plasma modes have been discovered in different materials, magnetic materials, anisotropic materials, and periodic materials. This all for about history of surface electromagnetic waves. Now, then let's consider a slab of material with thickness d, and if we go to limit of very thin dielectric slab, not obligatory dielectric, but every material with dielectric permittivity epsilon. And then in the limit of very thin layer, we can obtain these dispersion relations for Tm, transverse magnetic, and these dispersion relations for Te, transverse electric mode, where chi is the two-dimensional susceptibility of the material, and alpha is the transverse wave number, which governs the transverse profile of electromagnetic field guided by this two-dimensional layer. And for surface wave, alpha, real part of alpha transverse wave number should be positive, greater than 0. It means that it means that real part of chi should be negative for Tm mode, and real part of chi two-dimensional susceptibility should be positive for Tm mode. This is the condition, necessary condition for existence of these modes. And we can consider several two-dimensional materials, classical, for example, classical two-dimensional electron system, this Drude conductivity of this system, and you can see that imaginary part of conductivity is greater than 0, positive. It means that susceptibility, real part of susceptibility is negative. Therefore, no Te mode can exist in classical two-dimensional electron system. In two-dimensional system, quantum wells with some resonant states, phonons, excitons, susceptibility of this system is here, and you can see that it can be real part of this susceptibility can be positive as well as negative, but positive it is for frequency lower than the resonant frequency of this resonant state. So Te mode can exist in these systems with phonons and excitons, and these modes have been studied maybe 20 years ago. Now about graphene. Graphene is a gapless material. That's why in graphene, interband transition of carriers is very important. So the conductivity of graphene consists of intraband part, it looks like Drude part, and interband part here. Interband, real part of intraband conductivity is positive, inductive, but imaginary part, excuse me, but imaginary part of interband condition, transition is positive, negative, excuse me. So at some point, at some frequencies, interband part of the conductivity prevails, and the total conductivity, imaginary part of the total conductivity can be negative. This means that in graphene, transverse electric mode can exist under these conditions. And this graph demonstrates the dependence of conductivity, total conductivity of graphene, depending on normalized frequency. Yeah, I borrowed this graph from this paper by Mikhailov and Ziegler, published in 2007. And you can see that total conductivity of graphene due to interband transition can be negative, but imaginary part, but in very narrow frequency band, shown here by a light blue arrow here. So it means that transverse electric modes can exist in graphene, but in a very narrow frequency band, just a little bit low, with frequencies a little bit lower than double frequency of Fermi energy in graphene. This is because for higher frequencies, interband absorption is very important. So TE surface mode can be good surface mode. It just attenuates. But for low frequencies, the total imaginary part of the total conductivity is positive, and this is doesn't satisfy the condition of existence of transverse electric modes. This is what was known so far. So TE modes can exist. Their phase velocity is close to speed of light in surrounding media. So it's very rather fast wave, and this mode doesn't couple to plasma oscillations in two-dimensional graphene layer. This is pure electromagnetic modes. But further, I will try to show you that not everything is so bad if we apply to drift current bias to graphene. Here is graphene and the drift velocity, and we can obtain the general dispersion relation for this system like this. But if drift velocity is along the wave vector of surface wave or transverse to wave vector of the surface wave, then the non-diagonal components of the graphene conductivity tensor is 0, and the general dispersion relation splits into two independent dispersion relations for TE mode and TM mode. And TM mode is very well studied in previous years, and now we will be talking about TE mode. To solve this dispersion relation, we have to know the Z component of the diagonal Z component of the graphene conductivity tensor. And we find graphene conductivity tensor by using hydrodynamic approach. It is valid when the rate of electron scattering is the largest rate in the system. It should be much greater than rate of electron scattering by impurities or phonons, and also it should be greater than the frequency of the waves. And with this, in this approach, we can obtain the diagonal Z component of conductivity here. You can see that it's rather cumbersome equation, but what is important, it depends on the drift velocity. So we can tune the conductivity by changing drift velocity. And I should mention that this expression was obtained in approximation of ignoring spatial dispersion, because, as I said before, phase velocity of TE mode is very high, about the speed of light. Then we can justify the ignoring of spatial dispersion. But it is important, or even for zero or small wave vector of TE mode, conductivity, imaginary and real path depends on drift velocity. This is not the case with classical two-dimensional electron layer, uh, because for classical two-dimensional electron layer, its conductivity doesn't depend on the drift velocity for zero wave vector. We should take into account spatial dispersion to obtain dependence of conductivity classical two-dimensional layer on drift velocity. Is the consequence of the breaking of Galilean invariance in two-dimensional system with massless electrons like graphene. And this graph demonstrates that indeed imaginary part of the graphene that component of graphene conductivity can be negative in the entire terahertz range from 0.1 to 4 terahertz. It means that TA mode can exist in graphene with drift current in the entire terahertz range, not only in a very narrow frequency band as without drift velocity. And the real part can be also negative of the conductivity. It means that amplification of TA mode can happen in this a little bit narrower but still rather broad range of frequencies. Amplification can exist. And this slide demonstrates the dispersion of TE mode in graphene. It goes just closer to light line in surrounding media. What is interesting and maybe surprising that phase velocity of this surface wave can be lower and also greater than the speed of light. It's actually known fact for attenuated surface waves. And to the right of this slide, we demonstrate the absorption map in the structure with prism above graphene. External terahertz wave is incident from inside the prism, and we use the prism just to separate the transmission for small angles and the total reflection regions in this case. And we can see that we have very strong amplification or absorption resonances depending on whether we in the region of negative real part conductivity or positive real part conductivity. And this strong amplification in these points corresponds to lasing in these points, because a negative absorption coefficient tends to minus infinity in this case. It's self-excitation. We have self-excitation of surface electromagnetic waves in this case. And it happens when dissipative and radiative damping of this mode is equal to gain provided by negative conductivity of graphene.
Vyacheslav, you have 2 minutes before you finish. 2 minutes.
I just finish in few minutes. And next we consider two-layer system, and there are can exist electromagnetic surface wave guided by graphene itself and also by dielectric waveguide. And we can see a little bit complicated dispersion dependencies in this case. But also we can see lasing in the region of negative graphene conductivity, real part. It's instructed to compare single graphene layer and two graphene layers. And of course, for two graphene layers, the threshold drift velocity is lower because just threshold negative conductivity can be reached in two graphene for small conductivity of two graphenes is 2 times greater than conductivity of single graphene, also negative conductivity. And the last slide demonstrates dependence of absorption and amplification for different scattering of electrons in graphene. And you can see that this for smaller relaxation time, we have broader frequency range for amplification. And it means that this kind of instability, this kind of amplification is dissipative one, but it's very nature. No dissipation, no losses, there is no amplification in this case.
Sorry, we have no
And
time. You have a conclusion.
I will come to the conclusions, so I will not read them because I mentioned them during my talk. Thank you very much.
Thank you for your presentation, Vyacheslav. And we have one short, we can ask you one short question. And I have one. Does the substrate influence on the one layer or few layer graphene properties for surface waves? Is it significant influence or not?
You mean dielectric permittivity of the substrate,
Yes,
or
yes.
conductivity of the substrate?
Both.
Both. In this work, we didn't consider lossy substrate, but of course, everything depends on the electric permittivity of the substrate. In short, the greater the electric permittivity and the thicker the substrate, the greater the role of dielectric waveguide modes in this problem.
Okay, thank you. I see.
Thank you very
thank
much.
you again. The next talk will be presented by Kirill Zaitsev, as invited talk of super resolution terahertz imaging of biological tissues, recent achievements and challenges. Please.
Thank you. Thank you for introducing me. So I will skip this first slide. Here is outline of my talk. So I will first highlight how structural elements of tissues, how structural elements of tissues, what dimensions do they have as compared to the terahertz wavelength scale, and then I will pose a problem to study tissues with superior resolution at the terahertz range, and then I will move to our original developments, to our original terahertz microscopy modality, and to our results of studying tissues with superior resolutions and new insights into the terahertz wave tissue interactions which we made. So we deal with the wavelengths of hundreds of microns as shown here, and in this range, in the terahertz range, water plays a dominant role in interactions between terahertz waves and tissues. As you can see here on the right, absorption of terahertz waves by tissues many orders of magnitude higher in the terahertz range as compared to the visible range. So we use water as main endogenous label of tissue pathologies, and water limits considerably the depth of terahertz wave penetration in tissues by tens or even a few hundreds of microns. So we use terahertz waves to probe only the superficial tissues as shown here. And here is our review papers on Terahertz biophotonics, on Terahertz diagnosis of neoplasm, so I won't do in-depth review of this topic here. But I move to this slide. On this slide, we tried to show how the tissue elements looks at the Terahertz wavelength scale. So here we plot a ratio between the Terahertz wavelength of 300 of microns, which corresponds to 1 terahertz, and the dimensions, typical dimensions of the tissue elements, considering all tissues or the bottom tissues of the brain. And here you can see that majority of the tissue elements, such as cells, cell organelles, microfibrils, are very small at the Terahertz wavelength scale. So for such tissues, common Rayleigh scattering regime is observed, and everybody uses effective medium theory to describe Terahertz wave interaction with such tissues. So on the right side of this scheme, we can describe tissue with some effective dielectric properties, and we can measure this effective dielectric properties. We can study that of healthy tissues pathology and differentiate them using optical constants in the Terahertz range as a component space for this differentiation. However, some tissues might possess heterogeneities that are larger or that are comparable to the Terahertz wavelength, as also highlighted here. There are either above the diffraction limit of the free space optics resolution or below this limit, and these heterogeneities can lead to non-Rayleigh scattering of Terahertz wave, to the misscattering of Terahertz waves, and for such tissues, evidently some new theoretical approaches to describe Terahertz wave tissue interactions should be introduced. But these heterogeneities are quite hard to study at this time because everybody uses diffraction limited optics, common Terahertz pulse spectrometers, and this pushes the researchers both in Russia and abroad to study of these tissues with some innovative imaging modalities. And the easiest way to perform super resolution imaging, which can overcome the IB diffraction limit, is to use some principles of near field scanning probe optical microscopy. As highlighted here, you can see that you can research from common lens or mirror-based optics to some scanning probes or scanning apertures of different geometry. And in such case, the resolution is determined by the dimensions of this aperture, but not the aperture of the optical system. Evidently, you can make a very small aperture. This would greatly increase the resolution, but with an increase in resolution, you have a considerable drop of energy efficiency. So commonly, such systems provide around 0.50, 0.25 lambda resolution, where lambda is electromagnetic wavelength. And evidently some novel modalities should be introduced. We introduced this modality, so we developed a so-called Terahertz solid immersion microscope, which uses an interesting effect of solid immersion. So solid immersion effect can be realized when you use a common focusing system, which focuses electromagnetic wave in free space, but in front of the focal point, you should put a hemisphere made of very high refractive index material. In such case, in this hemisphere, we observe, like on this slide, a reflection of ordinary waves, reflection of we observe ordinary reflection, we observe total internal reflection, and for both ordinary reflected waves and for evanescent waves that are excited due to the total internal refraction, the wavelength is reduced by a factor of approximately N, where N is a refractive index of this high refractive index material. In our study, we realized our microscope based on the backward wave oscillator as a continuous wave Terahertz emitter, and a Golay cell as a detector of Terahertz wave intensity. And we use silicon as a material of hemisphere which possess refractive index above 3 in the Terahertz range. And this allows us to first predict numerically and then achieve experimentally almost isotropic resolution of about 0.15 of wavelength. So here you can see a resolution test on the right, and we see that it's even, it can be slightly higher. Obviously, this system do not use any subwavelength probes and apertures in an optical scheme, and therefore we only have the energy losses due to Fresnel reflections at the optical elements surfaces. Therefore, we have considerably higher energy efficiency of our system as compared to any other near-field imaging modality. And we then applied, we also tried to make our imaging modality quantitative. So we developed an approach to retrieve from the imaging data the spatial distribution of the local optical properties of a sample at each imaging point. Here you can see some outline of our algorithm. And here you can see a test of how this method works. So we can, at each point of the image plane, we can measure refractive index. Here you can see that we apply a few test objects to study how we correctly retrieve the refractive index. This is a mixture of propylene glycol with water with known refractive index from spectroscopic data. And we see on the right bottom panel that our predictions correlate well with the prior knowledge of refractive index when we measure such a liquid samples with our microscope. And then we applied it to study tissues of different kind. First, we start from brain tissues. Here is Terahertz solid immersion microscopy of intact rat brain and brain with glioma model. Xenograph xenotransplanted glioma model, which has a very diffuse margins and which is heterogeneous in a similar manner that that is glioblastoma of the human brain. So it mimics glioblastoma of the human brain. And you can see on images of intact brain tissues, of brain tissues with a tumor, that along with a difference in the Terahertz response of tumor that is observed on the bottom panel, both in ordinary Terahertz image retrieved refractive index, absorption coefficient, and even estimated water content, we see that both tumor and both intact rat brain is very heterogeneous. So we observe mesoscale heterogeneities of tumor that are associated with accumulations of tumor cells, hemorrhages, areas of necrosis, and we also observe heterogeneities of intact rat brain that are attributed to different response of white matter, gray matter. We clearly observe different response of cortex and white matter here, and to other neurovascular structures. And this shows that indeed when we apply Terahertz pulse spectroscopy to measure such a tumor, we also observe differences between intact tissues and the tumor, as everybody does. But the observed dispersion of measured properties is attributed to these heterogeneities. So these heterogeneities gives us quite large variability of the measured effective optical properties. We also can image not only the heat-rated freshly exist tissues as shown on the top panels, but dehydrated tissues which are embedded in paraffin block. So after paraffin embedding of tissues, we remove all water from tissues, and we remove all contrast from our Terahertz images. This is an evidence that water plays a dominant role in formation of the Terahertz response of tissues. and in the observed contrasts between intact tissues and the tumor. Here we show Terahertz spectroscopy of intact tissues and tumors of the brain, gliomas of the brain of the different VHO grade. And I would like to also highlight that in our measurements of brain tumors, we observe a very large dispersion of the measured optical properties. And this dispersion is attributed to heterogeneity of tissues, as we now known from the solid immersion microscopy data. We can move to imaging of other tissues. You can see here on the right, for example, imaging of freshly accessed tissues of the human breast, which is intact fibrous connective tissues in which separate fat cells are embedded, as you can see on the right. So this fat cells has the dimensions of around 0.2 of the wavelength, and we observe these fat cells on our Terahertz images as separate elements with completely different response. They have lower refractive index, lower absorption, because fat contains much lower water as compared to surrounding fibrous connective tissues. These are also other images of breast tissues where you can see different scatterers. On the bottom you can see images of muscle from tongue. So when we're now trying to study other tissues in using our solid immersion microscope, we observe that all these tissues, almost all tissues, contain some structural elements that should lead to the scattering of Terahertz waves. And for such tissues, these images doubt applicability of the effective medium theory and all simplified approach that are nowadays applied to describe Terahertz wave tissue interactions. So we can see that we can take fat tissues and fibrous connective, fat cells and fibrous connective tissues, and calculate using the Lorentz mean scattering theory parameters of Terahertz wave scattering on such a separate cells. You can see that here are differential scattering cross sections or indicatrix of Terahertz wave scattering on a single scatterer. And you can see that these indicatrix are all non-isotropic in nature. They are completely non-Rayleigh indicatrix. So therefore, for such scatterers, we should develop some interesting approach. We have now submitted a paper where we tried to introduce some radiation transfer theory to describe interactions between Terahertz wave and such tissues. So I won't talk about it too much, but interestingly that for such system we cannot develop radiation transfer theory using basic principles of this theory from optics, because when we have scatterers, when we have lossy scatterers or non-lossy scatterers and non-lossy host medium, non-lossy matrix, there is no problem with radiation transfer theory. But when we move to such system where we have both lossy host medium and lossy scatterers, it's principally impossible to develop such a theory without any approximations. It's quite an interesting situation that we observe in the Terahertz range. So we developed other approaches. So we took our microscope and we tried to make it polarization sensitive. So we introduced in our optical scheme polarizer and analyzer, which are based on freestanding metal wires, as shown on the left top corner of this slide. And we tried to imaging brain tissues in a polarization sensitive manner. So here you can see that intact red brain was taken, and we oriented our images so the electric field vector is collinear and transfers to the corpus callosum of the brain, so this area of the brain, which is formed by, as shown on the left bottom corner, by a bundle of axons that bridges the cerebral hemispheres. And we observe quite interesting effect for the first time. The effect of tissue birefringence or structural optical anisotropy of tissues is well known in the visible optics or infrared optics, but it wasn't observed till now in the terahertz range. And here we've shown that corpus callosum, which we can see here on the maps of refractive index of tissues, shows quite different response for the two electric field vector orientations. And here are some calculations of the refractive index distribution along this area of the brain. And in this setup allows us to observe this effect for the first time in brain tissues. And now we are showing that such effect is quite interesting, and it could be observed in all tissues that has a fibrous structure. So this paper should be published, I guess, within a month or two. We're also trying to achieve better performance of our microscope to boost its resolution, and we try to find material which has even higher refractive index as compared to silicon. And we found such a material. So here you can see almost the same configuration of our solid immersion microscope solid immersion lens, but this lens with an equal geometry is made of rutile, titanium dioxide monocrystal. And this monocrystal has a very high refractive index in the terahertz range, so it can be as high as 10 or around 8. And we've shown that if we made a lens of such a material, we can use equal configuration, and we achieve a resolution even higher than was previously observed. It is around 0.06, 0.11 of wavelength, and it is anisotropic due to a number of factors. So we have just this paper just accepted for publication. So this is our research group, main collaborators who participated in this work. So thank you for your attention. That's all.
Thank you for your interesting talk, and we have one short question. Yes, please.
I'm sorry. So you study very small spots of tissues, and they are less than the wavelength. Yes, and you see the refractive index and absorption coefficient, which usually are introduced to characterize not in the far field zone the tissues. What do you think if the spot will be more and less than in your case? Will these characteristics change? Mm-hmm. So how absolute are these characteristics? How character they are directly to these materials, but not to your system, optical system?
I understand the question. So we're not the first who tried to attribute some effective optical properties to the subwavelength scale elements, because there is a Peter Jepsen group who studied, for example, graphene conductivity with even nanoscale resolution. In my opinion, there is one possible source of discrepancy between the measured properties of large objects and small objects. When we image tissue, we assume that at each position of our microscope system, the tissue is homogeneous. So we assume that within the focal spot, within the depth of field of our system, this tissue is homogeneous, and we characterize this homogeneous volume. Evidently, if we observe some margins of different tissues or some scatters within this volume, we can have some source of noises of discrepancy. But evidently, we take this the approach of the effective medium theory actually, but applied it to much smaller scales of tissues.
So if this spot is larger, yes, and the material is homogeneous, you will obtain the same result.
Yes, we've shown it because actually when we try to make our microscopic images, first we tried some test samples with a non-refractive index. We tried some tissues which was primarily characterized. And our microscopy data corresponds well to the spectroscopy data, but when we measure heterogeneous objects, spectroscopy gives us confidential intervals due to this heterogeneity. In microscopy, we see this heterogeneity and we can characterize it. So that's the point. But if the resolution will be higher, maybe we will find some more interesting results. So
Thank you, Kirill. Thank you very much. And the next topic will be presented by Dr. Tarasenko from IOF Institute, St. Petersburg, H currents induced by terahertz radiation in two-dimensional systems.
I will speak about photoresponse of a two-dimensional electron gas to structure at Terahertz radiation. How to switch? Yeah, the key persons who are involved in this activity, there is no pointer. Yeah? This is Alexey Gunyaga, this is our student, master student, and Dr. Mikhail Durnev. So they did the most part, the major part of the work, and I just present the results. It's very convenient. So I'll speak about photocurrents induced by structured terahertz radiation. So we are interested in the photocurrents, which is proportional to the radiation intensity, photocurrents induced by terahertz radiation. And I think that there is not necessary to talk that this is very important for the development of detectors of terahertz radiation, and terahertz radiation, terahertz spectroscopy is an important tool for the study of electron kinetics, different processes in solid states, and so on. If we consider the photocurrents induced by homogeneous radiation, for example, just by the plane waves, that we need some kind of symmetry breaking, which indicates the direction of the current flow. And this can be microscopic in homogeneity. For example, we can speak about pin junction, asymmetry of contacts, quantum ratchet, and so on. Or, for example, this asymmetry can be hidden in at microscopic level, for example, in the crystal structure. Then if crystal structure, like the center of space inversion, we can also have a photocurrent by terahertz radiation. Or additionally, if we apply terahertz radiation at oblique incident, then we can cause a photon drag, the drag of electrons, and this is also produced current. But in generally, these mechanisms of the current radiation then require asymmetry of structure, and this is different type of asymmetry. However, we can think also about the generation of photocurrent where the origin of asymmetry comes from the radiation itself rather than from the structure. And in this case, we can speak about structured radiation. This term structured radiation, now it's widely used, and more or less it means that we deal with anything except just plane waves, just homogeneous radiation. The simplest examples are just, for example, intensity grating. If you put two light beams on the two-dimensional plane, then because of interference, you can have a intensity grating. Or if you use, for example, two plane waves with orthogonal linear polarization, then as a result, you have a grating of polarization grating. And this is widely used in spintronics to generate spin grating. Or in more general, we can, now it's available different types of optical beams. For example, optical beams carrying orbital angular momentum. They're called twisted light. This is when you produce, okay. This is, I try to use pointer, but It's not possible. So in this case, you can produce a special kind of beam, and this beam is characterized by orbital angular momentum, that additional to the polarization of beam, you can transfer to electronic system orbital angular momentum. In all these cases, obviously, the radiation is inhomogeneous, so the symmetry is broken, and it's already enough to drive the photocurrent. And this is the aim of my talk. So I'm going to describe the photocurrent which is induced by inhomogeneous radiation. So we assume, okay, sorry, just again, we assume that the structure is radiated by monochromatic waves, but the amplitude of the waves, complex amplitude, it varies in the two-dimensional plane. For example, it can be intensity variation or polarization variation or phase. So any parameters of the light can vary in two-dimensional plane. And we are interested in the photocurrent, which is induced by this radiation. So we are interested in the DC current, photocurrent, therefore it should be proportional to the square of electric field amplitude, because this should be time independent. And we understand that this is possible only when the radiation is inhomogeneous. So in some case, there should be special derivative of this value. Now we can consider this type. And so it's possible to build quasi-classical microscopic theory of this effect. So we consider that we have a two-dimensional electron gas, which is excited by structured Terahertz radiation. The electron distribution, the electrons are described by electron distribution function, which depends on the electron momentum, position, and time. And then we can solve the Boltzmann kinetic equation. This is Boltzmann kinetic equation, and here is electric field and magnetic field of radiation. Importantly, we should take into account that in radiation there is not only electric field, but also magnetic field, which are related to each other by the Maxwell equation. For example, if we assume that electric field is homogeneous in the plane, so there are time derivatives, then necessarily we have a magnetic field, out of plane component of magnetic field. This is just some kind, it follows from the Maxwell equation. And then we should take into account in this Boltzmann equation both electric and magnetic field. If we deal with perfect two-dimensional electron system, then only in-plane component of electric field and out-of-plane component of magnetic field are important for the electron transport. Then we can solve this Boltzmann equation to the second order of electric field, to the first order of light intensity. We assume that the length of the field variation is much larger than the mean free path, and this is typically true for the terahertz spectral range. And then we can obtain these equations. So this is the final equation for the photocurrent induced by structured radiation. And now I'm going to explain a little bit. So we obtained that there are three contributions to the photocurrent. They're indicated here. One of them, we call it photothermoelectric effect. This is contribution where the current comes from the gradient of the intensity. So as 0 is the intensity, it's just a square of the electric field amplitude. It is 0 Stokes parameters. So it means this current originates from inhomogeneous heating. So if we excite the sample with radiation with inhomogeneous intensity, then we have inhomogeneous heating, and it produces thermoelectric current. And this is thermoelectric current. In our case, just this thermoelectric effect is caused by optical excitation, therefore it's photothermoelectric effect. In addition to this current, we have a photocurrent which depends on the polarization. This current is driven by polarization gradients. So you can see that it's proportional to the space derivative of polarization Stokes components, S1, S2, and S3. They are shown here. These two Stokes parameters, they describe linear polarization in the XY plane and in the diagonal plane. And this is third component, third Stokes component, which describes the circular polarization of the light. And you can see that special variation of all these parameters can induce electric current. And finally, we have a third contribution, which is not reduced to this, nor to this. This current is caused by gradient of phase of electromagnetic phase, because in fact these terms, so this is also space derivatives, it's somehow proportional to the gradient of phase. And we can consider this as a generalization of the photon drag effect, because the simplest case when we can have radiation with a phase gradient is the use oblique incident of radiation. In this case, the intensity is homogeneous, the polarization is homogeneous, however, the phase of the electromagnetic field depends on two-dimensional plane. And it's already enough also to drive the current. Therefore, this contribution can be seen as a generalization of this photon drag effect. And now just a couple of examples how this current can be produced. For example, for the current driven by polarization gradients, we can consider two-dimensional structure when we excite it with terahertz radiation, and the polarization of this radiation varies in the plane. For example, it can vary from linear along x to linear along y, as shown here. Or for example, we can use radiation where polarization varies from sigma plus to sigma minus along this. In this case, so this polarization gradient drives electric current, and here show the x and y component of this current. For example, if the polarization plane rotates, then you can see this distribution of the current. The current emerges only in the area where polarization varies. Yeah? And on average, these particles flow from this part of the sample to this part of the sample. If we have just this situation where the polarization varies from sigma plus to sigma minus via linear polarization, then the currents between domains excited with opposite circular polarization, it flows predominantly along the boundary of these domains. And the direction of the boundary depends just on this polarization. Interestingly, that in high frequency limit, this photocurrent more or less independent on the momentum relaxation time, and it's also independent on the profile, how you vary polarization. So it depends only initial and final polarization. And in this case, it can be attributed to the kind of topological current where topological indexes of different domains are opposite. And finally, I would like to apply this theory to the twisted radiation beams. So I already mentioned that twisted radiation is beams which carry orbital angular momentum. And one of example of these beams is a Bessel beams. You can see it as a beam which is composed of plane waves, and the wave vector of these plane waves, they align on the surface of conic surfaces. So this Bessel beam is constructed by the plane wave with a wave vector q and some polarization. And this wave vector just fills the conic surfaces. And this is just the expansion of this Bessel beam over the plane waves. And importantly, this coefficient, this expansion coefficients, it has a very specific dependence only on the angle phi. Phi is the azimuth angle of this cone. And here you can see that this is integer number, m, and this integer number determines the projection of the total angular momentum. So if m zero, that's zero momentum, and if m quite high, so you have this special beam. Now, if you sum up this equation, you can calculate the components, radial and azimuthal components of the electric field in the beam. And this is shown here, so it's given by the Bessel functions. That's why these beams are called Bessel beams. And this is just example on the cross-section of electric field distribution in one of the Bessel beams. Bessel beams are interesting that they are not diverging. So I mean that this profile holds, so it is independent on the position. This is also this beam. They are not diffractive. In these Bessel beams, obviously, the electric field, both intensity of electric field, polarization, and phase may depend on the position, and therefore these Bessel beams also produce electric current, photocurrent. And here I show just example of this case. So we consider the radial Bessel beams with the integer, this number plus minus 2. This is distribution of electric field in the beam. This is snapshot of electric field distributions. So because electric field is alternating and the electric field distribution at any time can be obtained just by rotating this distribution counterclockwise or clockwise. And this is the resulting photocurrent, DC photocurrent, which emerged by these Bessel beams. You can see that photocurrent have both radial and azimuthal contribution, and azimuthal contribution is direction, depends on the sign of this parameter. So the photocurrent forms kind of vertices, and the direction of vertex depends. So in all parameters of the photocurrents, they're determined by the parameters of the Bessel beams. Therefore, that can be used to extract the parameters of the Bessel beams. And here's just my conclusion. The conclusion is quite simple. The conclusion is that structured Terahertz radiation can induce photocurrent, even in homogeneous two-dimensional system. And there are three contributions to the photocurrents. Photocurrents can be driven by radiation intensity, gradients of Stokes polarization parameter, or gradients of phase. Thank you for your attention.
Thank you very much for interesting talk, and we have time for several questions.
I have some question about non-homogeneous polarization case. Have I understood correctly that these currents are not stationary? I mean that when you obtain non-homogeneous current, you will get a charge accumulation and you will get electric field which compensates this current.
Yeah, thank you very much. You're absolutely right. So this is photocurrent induced by the radiation. But if the divergence of this photocurrent is non-zero, it means that this will be charge accumulation. And it means this additional charge produced static electric field. This electric field causes the current which will compensate. So it will be drift current. Yeah, and in fact, I just do not show, but we also calculated the special distribution of electrostatic potential caused this fact. Yeah, yeah. Definitely the charge should be conserved. Yeah.
Thank you for your talk. I have a question or maybe an idea. In such devices and Terahertz photoconductive antennas, for example, we need some asymmetry when we apply biased field. And a problem of biased field, for example, when you apply photodamper effect for generation is not solved. Yes, and could you use your approach to calculate how what current will we observe when we try, for example, to detect Terahertz with non-biased antennas? Is it possible?
Yeah, I think it's possible. I have a long experience collaborating with experimentalists, and I know that sometimes it's not that easy to explain and to reproduce all findings that they observed. But in principle, yeah, why not? It's just standard tasks of electrostatic electrodynamics. Yeah.
Oh, thank you.
Thank you.
Thank you for good explanation of a theory. Have you got some structures of the surface which prove your results of calculations?
So I do with theoretical physics, and for me it's quite easier just to show some equations. But in fact, I think this is experimentally possible. I show some references that, for example, structured radiation in the terahertz spectral range is already somehow, they can produce it already. Yeah. So there are some papers where people observe similar effect in optics. For terahertz radiation, I'm not aware of any references where the people observe photocurrents induced by structured terahertz radiation. But for us it's good because it allowed us to be the first in this field.
Thank you very much. And we have no time for questions.
Thank you. Thank you.
And the next topic will be presented by Galia Kitaeva from Lomonosov Moscow State University. Prism lens couplers for efficient sideways Cherenkov Terahertz wave generation in non-linear crystals.
И на что нажимать? Непонятно. Что-то как-то нет. Не работает. Ага. Окей. So thank you for the kind introduction. I'll tell about the work which was done in our quantum optical terahertz lab in the Moscow State University. But today I'll tell about effect which is far from quantum effects. It is pure classical one, and maybe you know it very well since it is the famous sidewave Cherenkov terahertz generation. It takes place in the nonlinear optical crystals under optical femtosecond pumping due to optical rectification effect. Usually the crystals of lithium niobate with high nonlinearity are used in these schemes, but the situation is that we cannot arrange the collinear phase matching generation in this crystal, and some arrangements are necessary, tilting of the pulse front or focusing of the pump beam into the line, into the slab, thin slab inside the crystal. I'll tell about the second way, about this line focusing, pump focusing systems. And the terahertz generation in lithium niobate in this case appears at the so-called Cherenkov angle, which depends on the directions, on the values of the phase velocity of terahertz waves and the group velocity of the pumping beam. It is a very famous scheme. Many people worked studying this scheme, and usually the terahertz radiation is extracted from the crystal using the silicon prism adapter, first proposed in Japan group of Hiramasa Ita and Kode Kawase. Also, it was from this lab. And now it is these silicon prism lenses, due to high, due to low absorption of silicon, high resistive silicon, and due to other famous properties of silicon in terahertz range, this scheme for tens of years remains the same. But in the Kode Kawase's groups, new works appeared where they showed where they used not flat prisms, but the prisms with specially shaped convex output surfaces. They can be spherical, as in this work, or conical shaped ones, as in the second work, and the results were very good. However, the authors do not give any idea why they chose these shapes of the output surface of the adapters, and how to calculate the optimal shape which can increase the output terahertz generation efficiency. And our work was aimed to propose some approach for calculating optimal shapes, and to compare we compared our results with the experiments, our experiments. Here, first I'll tell about the experimental setup. It is the common terahertz time domain setup. We use the erbium femtosecond laser. The terahertz generation is detected by commercial photoconductive antenna, and our crystal of magnesium doped lithium niobate was supplied by the common silicon prism, but we implied different planar spherical lenses. You can see here them. Is it seen? Planar spherical lenses. So the distance between the output surface of the prism and the input surface of the lens is very small in comparison with the terahertz wavelengths. So we can say that we have the adapter with the convex output surface. The geometrical parameters of the lenses were different. You can see here them. And in experiment, they have shown different results. So the temporal profiles, you can see them to the left, and the Fourier transforms give us the power distribution in the spectral region. Our detector was able to detect up to 2 terahertz only the radiation, and you see even in this case the lens adapters are sufficiently better than the pure flat prism. The data for the flat prism are shown by black curves, and these are distributions from different lenses. Now, how to consider what takes place in case of such a convex adapter. First of all, we had to model the processes which take place inside the crystal. Inside the crystal, we use the special approach where we consider the effect of optical rectification as a continuous set of the 3-wave processes of interaction between different spectral and spatial components of the pumping wave, plane components of the pumping beam. We consider that the spatial distribution has a Gaussian shape inside the crystal, and 2 frequency components with frequencies omega 1 and omega 2 shifted by some terahertz fixed frequency give the terahertz radiation in the plane wave directed according to the transverse phase matching conditions. This condition should be satisfied for transverse projections of the wave vectors of the spatial components of the optical beam and of the terahertz wave. So after integrating all these signals obtained from different 3-wave processes, we can obtain the terahertz field generated in a given direction, and then the angular distribution of the angle power density, frequency and angle power density. Here the theta is the azimuthal angle, polar angle, polar or radial angle of direction of the terahertz wave, and phi is the azimuthal angle directed. So in respect to the direction of the pumping beam. And these are results which show how the terahertz radiation is distributed inside the crystal in coordinates phi and theta. If absorption is not taken into account, the polar distribution along the polar angles is rather narrow, but different azimuthal directions also give their impacts into the terahertz beam. So the broadening along the azimuthal direction is very high always, but if we take into account the crystal absorption, the broadening becomes more in the polar direction also. But please pay attention to the color scale in here, in these pictures. You see that when we introduce absorption into the calculations, the intensity, the peak intensity, drops down very, very fast. And this situation can be improved if we focus the terahertz, the pumping beam into the smaller spot. This is the diameter of the pumping beam. These effects are very well known for this type of generation. We only show how our method can explain the experimentally obtained results inside the crystal. But this radiation cannot totally be extracted from the crystal due to the total internal reflection effects inside the crystal, even with the adapter. So what will take place if we consider the same radiation, even in case of no absorption, at the second step, after passing through the boundary between the crystal and the silicon adapter. And please, you see broadening, some broadening also takes place, but the intensity is not decreased so much at this boundary. But if we consider the flat prism and see how the terahertz generation will be distributed outside this prism, we see that the broadening along the polar angles increases very much in a high degree, and the intensity goes down. Intensity, even in the maximum, at the Cherenkov angle, is sufficiently less than in case of what we have inside the crystal. So the losses are very high. The losses are very high, and you can see how important it is to diminish these losses. Obvious, and of course, to decrease the angular distribution, to collimate somehow the radiation outside, to be able to focus it then to the detector or object under study. So when we consider the more complicated case with the lens imposed to the flat prism, we see that the situation can be improved if the lenses are taken with some special values of these parameters. This parameter is the distance between the pumping beam and the centrum of curvature, its ratio to the radius of curvature. In this case, we consider only the radiation which appears in one point inside the crystal, intersection at the axis of the lens. Of course, it is the limitation of our approach in case of the spherical lens, but if the shape is conical, it will not be so bad. So first of all, let's see and what was published before for the conical surface. Surprisingly, we found the paper where this conical surface and its geometrical parameters were described in detail, and directly our Japan colleagues really make the conical surface with this parameter, where the intensity is the highest one, but no papers. How did they calculate it? Then let's compare with our experiment. These numerical modelings, calculations were done directly taking into account the parameters of our crystal, of our prism, and so on. Dispersion of the crystal was detected measured specially before. So what is inside the crystal and what is in the outer space, at the air, after passing through the flat prism. You see how small is the intensity and how broad is the angular distribution. Then lens number 3 slightly improves the situation. The lens number 1 gives a very good result concerning the intensity in the maximum, quite the same as in the crystal. And it is due to, of course, it is due to collimating of the beam at the output of the crystal. And the best lens is number 2, where the beam is collimated in the narrow, within very narrow angle, and the intensity in the maximum, of course, is much more than inside the crystal due to concentration. So it is the density, the angular density. To compare with the experiment, we integrated this density distribution across the angle of detection of our system, and obtained the not power density but the power. So you can compare the results of the experiment and theory, and you see that in theory the lenses number 2 and 3 are 2 and 1 are better. As an experiment it was obtained, but the effect is not so high in experiment as it predicts the theory. We suppose it is due to the fact that in our calculations we consider only one generating point. Other generating points which are not at the axis of the lens, it is more difficult to, maybe in future we will do these calculations, but numerically. However, we see that this approach, even simplified approach, gives the same result as an experiment concerning the lens. That lens number 3 is not good, the prism is not good at all, and we think that this way of calculations have some future, can be implemented in future. So in summary, I described you here the theoretical approach for calculating the angular power distribution. So by integrating solutions of the nonlinear wave equations for individual spatial modes, considering subsequent transformation of differently directed Terahertz components and the propagation through the boundaries of the adapter, and it can be used.
Thank you for your talk, and we have time for questions.
Thank you for the talk. In the introduction part of the presentation, I have seen the scheme of other authors, and they have used periodically pooled lithium niobate crystals, so this periodical domain structure.
It is not. It's not so important. So due to periodical pooling, we only shift to some direction the phase matching direction.
It will not allow to increase the power of generated.
No. Phase matching, periodical phase matching uses only spatial harmonics of chi2 distribution inside the crystal. They are less than the total chi2 value. So some decrease of non-linearity we always have if we use the periodically pooled crystals. And in this scheme, this periodical pooling is not necessary, and it decreases the spectral widths drastically. So it's not important here.
Thank you for your talk. First, I want to ask Koda Kawasi in his work nowadays. I saw that they generate quite effectively spectra from 0.5 to even 5 terahertz. What couplers, decouplers, do they use nowadays? Do you know in their setups?
So they use different couplers, but the best couplers are conical ones.
Conical, yes?
Yes.
And are you planning to optimize further your couplers for your work? Because it's quite an interesting engineering problem, I think,
Yes.
for optical.
If anybody can help us in fabricating such conical elements, we will do it. It will be very effective.
Thank you.
So.
Thank you very much, and we have no time for other questions. Thank you, Alia. The next talk will be presented by Dr. Shurakov from Moscow State Pedagogical University, and the topic will be Terahertz hot electron bolometer based on chip spectrometers for material and biomedical studies.
Hello, dear colleagues. Well, I've been just introduced, but well, it never hurts to introduce yourself once again. So I'm Alexander Shurakov. I'm with the Radiophysics Lab at Moscow State Pedagogical University. So the work described during this talk was done over there. The work entitled, well, it is devoted to HEB based on-chip spectrometers for different types of spectral studies. And let me just proceed to motivation of this work. So this slide well describes content of my presentation. So basically what I'm gonna do, I'm gonna describe motivation for the development of particular hardware implementation of a spectrometer. So then I will just provide a very basic idea and some recent results in terms of how we do and what we do and what we achieve. And then in the end, we will see what is technologically feasible and what is the technology that we have at the moment at our lab in our university. So, well, this slide is quite a standard one, but I cannot omit it. So it says what's important. So the technology of terahertz, well, hardware implementation is now at the stage that it can be used. Well, practically, it comes to the use in everyday life experience. So in terms of applications of terahertz spectroscopy, right, so we can use it in a number of applications such as security systems, medical diagnostics, and agriculture, material science. And since my talk is more about hot electron bolometers, HEBs, as was previously referred to, we're rather from the field of radio astronomy because, well, hot electron bolometers well have been proved as perfect candidates for spectroscopic observations at frequencies above 1 terahertz for radio astronomy applications. So, well, in principle, what we can see, well, since we talk once again about radio astronomy and its applications, so in terms of popular solutions for radio astronomy in the lab, you can rely on a bulk and very nice and easy in use Fourier transform and diffractive grating spectrometers. They have their certain pros, they have certain cons, and first of all, they're bulk, slow, and not well, not that easily to use on airborne space missions and so on. Well, well, this issue is resolved if one relies on heterodyne spectrometers. So there is a number of, well, there is a variety of terahertz spectral instruments in radio astronomy that made use of Schottky diode, SIS, HEB mixers. So, well, examples of room temperature and cryogenic detectors that can be operated starting from Kelvin range to room temperature operations, and they are compact, fast, but yet they narrow band, and they rely on coherent detectors, so sometimes it's not that easy, not that trivial to use them to implement the circuitry, and the higher the frequency, the bigger the efforts are. So as an alternative, so recently reproposed filter bank spectrometers. Well, actually I've been just attending a lecture of a guy who was at the very beginning of VLBI, very long baseline interferometry, and he said that the first type of spectrometer that was implemented, he said, in Russia, okay, it was a filter bank spectrometer, and once again, a filter bank spectrometer comes again back, so it is reproposed. So, well, it provides a compactness, it is quite fast, it is relatively wideband. Well, it has to rely on quite multiplexable direct detectors. And here we can see that among the detectors mentioned on the slide, we can see, well, MKIT detectors, HEBs, and so on, and those are the candidates for the sensitive elements of such spectrometer or not. Okay, it actually depends. So, but before we go to that, why filter bank design? So once again, it is driven by the needs of modern radio astronomy, which which is focused on the study of the universe formation processes. And for this task, well, it is proposed that spectral instruments with moderate spectral resolution, roughly 50, 100 or something like that, can give number of positive contributions to the possibilities of hardware being used in spectroscopic measurements. Okay, so here we have number of motivations related to the cases of studying structure and star formation processes, the universe evolution, and the galaxy redshift, and so on. Okay, so so existing solutions of filter bank spectrometers that exist so far, they rely on MKIS detectors, microwave kinetic inductance detectors. So here to the left you have a compact waveguide implementation, to the right you have a superconducting on-chip implementation. Both rely on arrays of kinetic inductance detectors. Well, they operated in the lower part of the terahertz band, starting from 100 to 300-400 roughly. So the operational bandwidth is nearly octave wide. And actually they have not that huge number of beams, so 50 beams roughly, and the spectral resolution is 20 to 300. So the key feature is that since we have such a number of detectors, since we have this filter bank, the detector has to be quite multiplexable. Microwave kinetic detectors are known for that. The question is, what do we know about HEB in this sense? Okay, so if you want to multiplex array of HEB terahertz detectors, well, you can use a quite simple scheme. Well, it was tried by us nearly 8-9 years ago. So, well, you can use a probing microwave signal. It can be directed into the detector, and then the response can be read out, which in turn provides opportunity to probe the internal state of the detector in response to terahertz radiation incident to its optical input. So here on the slide we have a setup that can be used to provide feedback in terms of understanding linearity of the employed scheme and the achievable performance in this untraditional readout scheme implemented. Okay, so going further. Okay, so once again, in this multiplexing regime, when external bias source of AC or CW or microwave of microwave signal is used, we can have a zero DC bias regime and single DC pulse regime, right? So to the left you have a bias voltage characteristics and impedance voltage characteristics, which correspond to the understanding of what happens with the HEB device. So the key features and performance parameters can be explained briefly that when you use external CW source, you inject microwave signal into the HEB device. So the device is biased or pumped, if you wish, by this source partly, so the superconductivity is partly suppressed, and then in turn, change of the impedance of the HEB device in response to the variation of external terahertz radiation can be probed by the change of reflection coefficient, and registered CW signal is the marker or is the key indicator of the incident power at the HEB's input. Okay, so we just use this approach, we just use this schematic, and but here the sensitivity of the HEB is roughly 1 picowatt per square root hertz. It was the same as this was measured in the conventional regime, and the dynamic range measured for operating regime with DC bias was 30 dB or beyond. Okay, so further, so here we have a sort of a bit interrogating slide, but yet the basic idea is the following. You have microwave frequency source. It creates number of frequencies. We can use the frequency sweep, for instance. Then it is directed into an array of on-chip HEBs, which are equipped with a wideband filter, wideband power combiner, and narrowband filter. So what we have to the moment, we have developed a compact SOI-compatible low-loss bandpass filters. They have fractional bandwidth of roughly 5%, so they can be tuned across the operating frequencies of 10 to 20 gigahertz. And this is suitable to implement multiplexing of, well, 2 independent frequency channels, octave wide, of HEB arrays containing 8 elements each. Okay, so So up to the moment, we have conventional designs of HEBs that rely on either waveguide design, quasi-optical design. The key features of the designs are provided over here. In both cases, we have narrow beam input optics. We have in one case horn antennas, in other case fisheye antennas with lens, and yet the sensitive element is integrated with on-chip circuitry or is placed at the plain antenna feed. The first design, the waveguide design, is good for direct detectors, right? So it can be used at frequencies of up to a few terahertz nicely. Then what happens, we will discuss next. And the second design is good at very high frequencies. It can be used even in the mid-infrared range and something like that, but yet it's good only for direct detectors and quite difficult probably to implement on chip circuitry. Let us see further why. Okay, so once again, we are going to develop, and we are developing a spectral instrument for upper terahertz band. Why it is a filter bank design we just previously introduced, and why we're aiming at the upper terahertz band. So, well, once again, since hot electron interferometers are first of all the candidates for spectral instruments and radio astronomy applications, we're driven by the possibility of measuring spectra related to the study of exoplanets formation, a balance of interstellar medium in the frequency band 7 to 14 terahertz. There are a number of windows with a decent transparency that can be found at the Antarctica site. So therefore, this is why this is the frequency of interest. Okay, but at these frequencies, if we talk about the classical solutions in terms of waveguides, right? So as you know, we can rely on metallic waveguides, we can rely on dielectric waveguides. Here we have a short summary on the main pros and cons of using hollow metallic waveguides, planar waveguides, and dielectric waveguide structures. So as you can see, if we just take a look at achievable losses at 1 terahertz, for the first type of waveguides, we can have hollow metallic ones, we can have few dB per centimeters. When we go to planar waveguide structures, it's even higher than that, and yet when we choose dielectric implementations, topological waveguides, photonic crystal waveguides, effective media waveguides, ribbon waveguides, or whatsoever, we actually have a very drastic decrease of losses, and also we increase integrability of the structures being developed drastically. Okay, so so what we have up to the moment, we have designed, implemented, and actually been studying at the moment, electronic photonic platform for Terahertz HB mixer. Pretty much it is based on the use of integrated silicon photonic crystals. So here on the slide to the left, you have the basic elements of such a mixer. So the NBN film is formed in the center, and the coupling is maintained through low-loss dielectric structures. So for such a developed implementation, we have a certain directivity parameters of input optics. So we have a 25 to 80 degree wide beam widths in the far field, and the ultimate insertion losses in terms of delivering the terahertz signal to HEB sensitive element, something of below 2 dB. Okay, so the structure is quite compact, and it is ready to use in terms of implementing more complex on-chip circuits. Okay, so the circuit now, the basic concept of the HEB based on chip spectrometer that we propose is provided over here. So to the left, we have a cryostat. Inside, we have a chip at 4 Kelvin. It consists of optical input interface, photonic power distribution lights, photonic filter bank with a Q factor of 100 roughly, and electronic photonic HEBs previously introduced. So once again, as I stated during the very first part of my presentation, we're going to implement 2 independent frequency lines to read out octave wide each. Okay, so in this case we have 2 options. We can just put a solid thin layer material at the optical input of the spectrometer in a cryogenic, and in this case we can measure cryogenic spectral properties of the material of interest, or we can have our gas liquid samples and surroundings, and then we can use a blackbody assisted measurement as provided on this sketch. Okay, so here, structural elements of the spectrometer are simple. So the optical input interface was previously developed, published, and verified. Photonic bandpass filters and photonic power distribution lines are of interest in terms of technological feasibility for the developed process that we have in the lab. And once again, the core element when we transform the modes of waves in the dielectric structures, in the electric currents in HEB, and microwave readout lines are also previously developed and evaluated. So the clean room process, what we successfully implement, we just use a Bosch process. We use basic splattering of metallic and superconducting films on soy substrates, and the key feature is that we can just create successfully the photonic crystal and effective media structures with the size that are provided in the lower left corner, right? So given that the operating frequency is something like 3 terahertz in our case, we have typical size of openings in the high resistivity silicon layer of the soy substrate, roughly 10 to 18 micrometers, and the period of the lattice of the openings is something like 20, 24. Okay, so in terms of what we can do in our technological facility, we wonder how this works out in terms of overall performance of the spectrometer that we can implement on chip. So to the left we have a wide junction that can be used as a part of the filter bank, well, as a photonic power distribution lines in front of a filter bank. So in this case we have a hole diameter and lattice constant for the periodic photonic crystal structure, similar to what we previously successfully implemented. Well, yet the structure in terms of simulations provides, well, it is feasible in terms of implementation, but yet it's not that wideband as we want. It's relatively medium loss, and it is not that easy to handle. So as an alternative, we just considered the implementation of effective media structure on quartz. In this case, we have to implement a 3 micrometer wide openings in roughly 20-30 micrometer thick substrate with a period of 4 micrometers. Well, it seems to be that we can try, we can have a certain positive results in developing such a structure, and yet in this case we have significant reduction of input losses and a significant increase of the input frequency band. So the design once again is feasible, it is quite wideband, and it is easy to handle since it is placed on 100 micrometer quartz substrate, can be installed in a cryogenic equipment and can be further used. Okay, so here we just want to talk about feasible binning and sensitivity of the spectrometer in terms of technological applicability and implementation prospects that we have in our lab. So the finalized wide junction structure in terms of the spectral properties is provided to the left. The preliminary filter design evaluated is provided to the right. So taking a look at the pictures, we can see and we can say that first of all, the Q factor of the filters can be increased to roughly 50-100, which is justified by the demands of modern radio astronomy instruments for spectral measurements. A frequency once again can be tuned in the band of interest. The band covers from 4 to 6 gigahertz if we talk about 3-0 loss in terms of insertion losses of the filter of the power distribution networks. So once again we plan and we can implement 60 pins with 100 gigahertz resolution, and given that we aim for black body assisted spectral measurements, we can ensure signal to noise ratio during the measurements of 100 if we rely on a regular performance of HEB devices being developed in the lab. Okay, and once again, the estimation and feasibility is provided, so all we have just to put things together, combine and justify whether it works as we predict or deviates from the predictions. Okay, so in summary, briefly, what was done. So during this talk, I just tried to motivate reasons for the development of filter bank on-chip spectrometer making use of HEB devices, and I tried to assess technological feasibility and achievable performance of such a spectrometer that is aimed for operation in the upper terahertz band around 5-7 terahertz or something like that. Thank you for attention.
Thank you very much for interesting talk, and we have time for questions.
Thank you, Alexander, for the very interesting talk. In the last part of your talk, you were just depicting the S-parameter dependence versus the frequency. Can you just comment several words about this study? Because I guess you were using a vector analyzer to study S-parameter, or it was something else.
Well, thank you for your question. Once again, no, we have just preliminary technological results in terms of capabilities, in terms of implementable geometry, and then based on this geometry we just performed electromagnetic simulations, parametric simulation, this is it. So we developed a structure, we defined tolerances, and these are the predictions with the geometrical parameters of the structures being technological, physical in our, well, implementable in our technological facility.
Any questions? Can you say about time constant of that modified hot electron bolometers? When you increase the sensitivity, what about time constant?
Yeah, this is a very good question. So actually it is defined by the frequency of probing signal, right? So since the frequency of probing signal is aimed to be in the range of 10 to 20 gigahertz, so we have to at least time twice the time corresponding to this frequency, right? So then we have 16 pixels, so we have to multiply. So therefore, well, microsecond scale at least, right?
Thank you. If no questions, we thanks again, speaker. And the next talk will be presented by Akhmat Khanov from Yekaterinburg Ural State University, and electrical field tunable diffraction optical elements based on lithium niobate single crystals.
Thank you for the presentation. Okay, my talk will deal with diffractive optical elements. We have heard a lot of talks about it, so I will remember you briefly. So there are two main types of these elements. These are amplitude mask and phase microrelief elements. In this talk, we will concentrate on phase microrelief elements. So they will allow to provide specially homogeneous phase shift of the current light passing through this element. And there are well, approximately three types. We can name three types of these elements. The simplest are double level, which just shift the phase by 0 and pi. Then multi-level, so you have some number of levels between 0 and pi, and elements with continuous phase change. And they are different mostly by, of course, efficiency of their work. So the basic method of their production is photo or electron beam lithography. These are high precision methods. If we speak about photolithography, it could be low cost for mass production, and so these are quite good elements. One problem is that the structure can't be changed, can be modified when you create this element. So it's absolutely stable element, not controllable, not tunable. And another approach which gives a hint on creation of some elements with some kind of tunability is utilization of Pokel's effect. We all know that this effect provides linear change of refractive index with change of with electric field, external electric field. It is widely used in optics, for example, for optical modulators or some deflectors. It's quite common technology, but in all these cases, as the electro-optic coefficient is the same as the whole volume of under the action of the external field, all you can you get is a homogeneous change of the phase of the whole wavefront. And another thing we have to take into account, and the idea is to use domains in ferroelectric crystals. So ferroelectrics are the materials with a constant value of spontaneous polarization, PS, on this picture. It's some analog of ferromagnets. And the main thing, okay, the regions with homogeneous value of spontaneous polarizations are called domains in this case. So on this picture, there are two domains with polarization up and down. And the most important thing that these domains have opposite side sign of electro-optic coefficient. And the second important point is that the domain structure can be changed by the action of external electric field if we apply a high enough electric field, higher than the coercive field. So the obtained domain structure will be stable for fields below coercive field. It will be stable for temperatures below Curie temperature of the crystal. So we obtain the quite stable object, which can be then tuned by electric field. So the idea behind this is as follows. We create some domain structure corresponding to our diffractive optical element. Without electric field on the left side, you can see it works just as a transparent plate. It just doesn't change the wavefront of light passing through it. But when we apply electric field, due to opposite sign of electro-optic coefficient, we get the change of refractive index in neighboring domains, and we change the wavefront of the element. So we have to apply the half-wave voltage for this element to obtain the phase shift of pi between neighboring domains. And what we eventually get, we get the double-level phase micro-relief diffractive optical element. As the material for this element, we will use the lithium niobate crystals. This is one of the main materials of nonlinear and integrated optics. They are produced in the large scale and quite cheap. So this is uniaxial ferroelectric. Then it means that there are only two orientations of polarization, up and down. It's uniaxial optical crystals. It has quite high coercive field and high Curie temperature, so the main structure will be very stable in these crystals. And if we look at the electro-optical coefficients in these crystals, they are, well, quite high, 10 and 30. Unfortunately, in the geometry I was showing you on the previous slide, we can use only this coefficient, R13. It's not the highest, but it's still high enough for applications. Okay, so to create this element, we have to first create electrodes pattern on the top of our element by photolithography, apply external electric field to create this domain structure, which required for particular element, and then remove electrodes and deposit the solid control electrode, the ITO electrode in our case, to control the work of this element. Okay, and at the last step we need to make annealing. Why do we need annealing? Because in this crystal there is an internal bias field which could be evaluated, measured by measuring of dielectric hysteresis loop, and it leads to the shift of the zero shift voltage of diffractive optical element. So to compensate it, we have to anneal it at some low temperature, about 150 degrees for 5 hours. And we will get element with very low internal bias field. So one small note on the domain structure. On the previous day, we have talk of Professor Schur about periodical domain structures for frequency conversion. So in that case, the domains should be strongly oriented in one direction. It's Y crystallographic direction. And the sizes of domains goes from 3 to 15 microns with very strong reproducibility of about 10th of nanometers. In the case of diffractive optical elements, we do not need such small domains. The domain size starts from 10s to 100 to hundreds of microns, but we need arbitrary domain wall orientation, which is important, and some sub-micron, in the best case, roughness of domain walls. So this is the elements we have tried to build. The first one was the simplest B-phase, B-level, double-level lens. This is a photo mask of photolithography, which is created by high-resolution photoprinting. So it's quite cheap mask of about $2 or $3. Then there is, on the right, there is a pattern in the photoresist, and further we can see the created domain structure in the optical microscopy. So these regions are domains of different sign. And if we analyze the accuracy of our structure, we can see that we have some errors indeed, which reach maybe 10 microns, and they are mostly concentrated along Y directions of the crystals, along these directions, 3 directions. These errors are related to some features of domain structure in these materials. The domain walls oriented in these directions are much more mobile. That's why they grow further. So to overcome this behavior, there are some approaches which can be used to increase the precision of the domain structure. The simplest one is the decomposition of required domain structure as a set of polygons with wire-entered domain walls, the most stable ones. In this case, we obtain some approximated structure of a diffractive optical element which can be created with high precision. And the other methods is improvement of techniques of periodical polling or correction of electrode pattern to take into account the features of domain structure. So the testing of this element has shown that it allows to focus the light with pretty good accuracy. The efficiency is 40%. This is close to theoretical limit for double level diffraction of optical element. We have some distortions, additional maxima here due to of C3 symmetry. This is due to domain shape distortions again, and they limit the possibilities to downscale this structure. And if we go and try to use the structure with approximated by polygons, we can get, well, we lose efficiency. Now we have got only 25% of efficiency, but this structure can be downscaled further, so we can make much smaller structures in this case. And another element, the second element we have tried to do is simplest B-domain structure to transform Gaussian mode into TEM01 mode. These elements can be used, and it was proposed in 2000 that these elements can be used for channel mode multiplexing. And this is the results of testing of this element. In a near field, if we test how it works in a near field, we can see that there is not only a TEM01 mode, but we can see some additional modes of higher order. But if we go to a far field, we can see pretty good TEM01 mode without higher order modes with half-wave voltage of this element is 3.6 kilovolts. And we can, if we combine two such elements in orthogonal direction, we can generate in an even TEM11 mode. Okay, the third element we have tried is an element or screw oxycon for generation of orbital angular momentum modes. This is a mask, photoresist. This is the domain structure of the element, and this is our element in a fixture with applied circuit for high voltage application. So when we try to work with this element, we have used two elements placed in series. They are arranged in opposite orbital angular direction. So when they both switched on, they have to realize the reverse transformation of the mode. These are results. On the left, you can see the results when only one element is switched on. We can see the formation of a mode with orbital angular momentum. When we switch both elements, we have got the reverse transformation back into the Gaussian mode. So this is just Gaussian mode with some small distortions. And what are the limitations of these elements? The first one we wanted to try is the response time of this element. And we measured the central peak intensity with response to field application. So, and we have got that response time, in this case, goes down to 300 nanoseconds. Actually, it was limited not by diffractive optical element, it was limited by photodiode bandwidth, which we used to measure this intensity. It's 10 megahertz. And actually, we know that lithium niobate is used in electro-optic modulators when the frequency goes up to tens or even hundreds of gigahertz. So we expect even lower response times. As for domain sizes, sizes of the element, well, we need to apply half-wave voltage for its operation, but if we exceed the coercive field, we destroy the domain structure. That's why we can estimate the minimal thickness of our element, and for typical parameters, it's about 150 micrometers. And as for lateral dimensions, they're limited by wafer size of lithium niobate. It's up to 5 inches now, and the external driving circuit. So we have to apply to drive the voltage to capacitive load with a capacity of about 10 of picofarads per square millimeter. And transparency range of element is limited mostly by the transparency of the control electrode, not the material itself. So the transparency of ITO electrode goes up to 1.8 micrometers. So it in current feels even the telecommunication wavelengths, and they can be used from visible to near infrared wavelengths. Okay, if we compare these elements with some closest analogies, as for example with liquid crystals, which also can be controlled by electric field, well, in our case we obtain lower switching times, much faster operation, lower minimal feature size down to maybe 1 micron, so in best cases hundreds of nanometers, and high transmission value, high optical damage, and we have only one big problem in this case. Well, it depends on application. We need much higher voltages for application, for utilization of these elements. Okay. And the future prospects is ongoing work of obtaining element with continuous phase change. In this case, we have to control not only the domain's formation, but domain growth in the polar direction. It's much more complex task. We have some preliminary results in strontium barium niobate crystals. That's also ferroelectric crystals, and with the feature of these crystals is a polydomain state with domain sizes about tens of nanometers, and we can create domain structure in these crystals by focused electron beam. Professor Schul told about this technique on previous day lecture, and this is some results. So this is domain structure visualized, imaged in the bulk by second harmonic generation microscopy. So this is the depth from the polar surface. We can see we have round domains at the top. They shrink and they disappear at the depth of about 150 micrometers. So what we have shown that the domain shape in this case mostly corresponds by distribution of polar component of electric field. In this case, so this is calculation of electric field, which goes to about the same value. So we can control, in some case, the growth of the domains, their formation in the bulk. Okay, and this is all. Thank you for your attention. I'm ready to answer for your questions.
Thank you for interesting talk.
Switch to this slide, maybe.
Have you questions?
I would like to ask a question about this smooth variation of the phase. So I wonder, is it possible to create a lot of small domains with a size much smaller than the wavelengths? And in this case, somehow this medium can be considered as an effective medium with a somehow average index. What is possible to apply in this case?
Yes, thank you. Well, as I told you, it is possible, I think, and even for these crystals, we have a domain size which is already lower than the wavelengths of the visible light. So we can try to play with them, to work with them as an effective medium. I didn't see this works, but we can try something. Yes, I think.
Thank you. And if no questions,
thank you.
Thank you again. And the last presentation in this section will be presented by Dr. Gavdish from Prokhorov General Physics Institute, Moscow. Terahertz infrared dielectric spectroscopy of astrophysical ices, recent achievements and challenges.
Thank you for introduction. I'm glad to be here and to present my work here, and not only my work. This is a huge collaboration work. So I will talk about some up-to-date results, our prospects, challenges of this SIM. And this work is done with our collaborators, mainly from the Max Planck Institute for Extraterrestrial Physics. So, briefly about the outline of the talk. I will start with the motivation, why it is relevant now. Then I will move to the experimental setup and its the processing of the TDS and Fourier transform infrared data. Then I will show you the last results in this field and finish my talk with unanswered questions related to research directions and some other questions if there will be from the auditory. Why it is important? Ices in the universe are one of the most common dense matter. Then up to 60% of the oxygen in space that is not included and incorporated in silicates is ice. So ices are very complex in space. You do not know maybe, but there are about 180 different molecular structures of ice in the space, different molecules. From such simple as water ice, CO ice, CO2 ice, to the organic species closely. Main part where you can find ice in the universe is nebulas and some protostellar clouds, like you can see the pillars of creation nebula here. When ices are incorporated as ice mantles on the cold grains, there are chemical processes that drives by heat, by atom bombardment, by UV radiation and cosmic rays. Then we have so much ices in space. In the last decades, the main focus in the observational astronomy moves to the terahertz and far infrared frequencies. So the SOFIA, Herschel, ALMA stations, space telescopes provided such data in this range of frequencies. While the laboratory spectra data are not so big in this part of the spectrum. There are nearly absence of the data in this region, and of course mainly there are no direct dielectric parameters of ices in this range of spectra. One of the reasons why it is so good to study the ices in space is that the formation of star systems is dependent on its chemical composition. Why it is so? Because of the Jeans instability. So the radius of the cloud, the radius of the instability of the cloud depends on its mass and its temperature, and the temperature depends strongly and directly on its chemical composition. Then this process is cyclical, and on all the stages of this cyclical process, there are much ice in such systems. So when we talk about dense clouds or accretion disk, there will also be ices that are interesting to study. Just some fun fact that first works that are in the terahertz range of frequencies were published in the Astrophysical Journal of, in the end of the 90s and the start of the 20th century. So it is somehow the scene that is very close to Terahertz community. Some words about our experimental setup. So you can see here the you can see here the cryostat. It is a helium closed cycle cryostat in the laboratory at München, and the construction of this cryostat is done in such way that we have optical access for the ice on the substrate, and the ice on the substrate is grown with a standard procedure in this field. So we have gas injection, the pipe in the bottom of the cryostat, and some periodic growth procedures, for example, 5 minutes deposition and up to 30 minutes total time deposition. The ice grows on the both sides of the substrate. The substrate and the optical windows are both made of the high resistivity flow zone silicon, so it is quite familiar for this field. Then you can see here the typical range of frequencies where we can work with a TDS setup. And it was very important to have the uniformity of the ice layer thicknesses. So we studied, because our cryostat, our cooler chamber, was mounted on the motor-controlled translational stage with respect to the Terahertz beam. So it was possible in this setup. We need some mathematical description of the propagation of the radiation through the sample, and here you can see the scheme of the reference and sample signals that we can have in our TDS setup. And there are some pulses, some satellite pulses in sample signal that we can also incorporate in our mathematical model, and as you can see later, it will be critical for having some initial approximations of the ice layer thicknesses, because there are no other ways to give it from other measurement techniques in such experimental setup. Familiar Fresnel formulas, Bouguer-Lambert-Birlow, are the base for all the construction of the mathematical model. And we finish with the theoretical and experimental transfer functions. And the error functional minimization gives us the dielectric or optical properties of our ices that we study. So what about initial approximations? As I said earlier, we have no ice layer thickness approximations from other techniques. Then we need to take it from our signals directly. So we use the positions of the peaks in the approximation that we have not so big dispersion of the characteristics. We can have this approach and self-closed system of the equations that will give us both the approximation of the refractive index of ice that we study and the ice layer thicknesses. We found that it is a very good approximation, so we have a linearly growing ice on our substrate, and it is very consistent for different regimes of the growing, so it is somehow the the reason that we use these approximations later. The next task, it was more complicated to have the broadband measurements when we use not only the TDS setup, but also the Fourier transform infrared spectrometer, Brooker here. As you know, in the Fourier transform infrared experimental setup, you have no phase information about the sample that you study. So you need to have some procedure that will merge the spectra from TDS and infrared ranges, and not only merge, but gives you the phase in the infrared range also. So you need, of course, the equivalent measurements in the TDS and FTIR regions, and then we can apply Kramers-Kronig relations in some modification. So if you have the phase in the TDS, then you have the constants. You have such constants as phi0 and phi1 for applying for the results of the Kramers-Kronig transformation, and then to have the phase in the broadband range of frequencies. So we move to results that we obtain using such technique and such processing. These are results for CO eyes. So you can see here 3 distinct absorption peaks, Lorentz-like peaks. We can apply the broadband dielectric model for such eyes to have the parameters of these peaks. Also you can see here some approximations of the detectable absorption level. It was done due to the absorption that is not zero between the peaks, like it can be from initial approximations. This detectable absorption level is such that the distinct absorption peaks are, of course, much higher than this level, and the absorption between the peaks can be associated with some noise and other distractions in the setup, probably. These results are for the CO2 eyes. So here are a bit more different Lorentz-like peaks, not 3 but 4, and the parameters for all the observed Lorentz-like peaks are presented here. What is here very important? First of all these results on the dielectric properties are obtained for the first time, as far as we know. Then we found these small absorption peaks in the infrared region that were absent in the literature before us also. This one around 8 terahertz, and these 2 ones also around 8 terahertz. The last part of these published results concerned about the accounting of the infrared waves that are scattered here in the infrared range. We think that we have absorption in the infrared frequencies up higher than 10 terahertz at this range. And to try to test this approximation, this assumption, we try to anneal the ices at different temperatures for 15 minutes. And we see that, first of all, for the CO ice, the structure has a higher order when we anneal it. So the peak at 8 terahertz can be associated with the structure, but not the properties of molecular composition, so not the properties of CO. For the CO2 ice, we also see that the order of the structure is higher for the annealed ice, but we cannot see such absence of the higher peaks. Maybe it is obscured by the growing of scattering in the ice and some other reasons. So these are our estimations. And the last part of my talk about the research directions. So we want to examine other ices, other ice molecular compositions. Then we interested in the study of porosity, of phase states of such ices under different conditions. We are very interested in the study of the scattering in such ices in the infrared region, because it will lead us to more distinct knowing of the ice structure in the terahertz region. So we will know the porosity, and we will know then the corrected dielectric properties of the bulk ice in this region. There are some unpublished results for the dielectric response of the N2 ice, for the dielectric response of water ice. Here for 115K, there also for approximately 10K. And there are some first results on scattering, when we found that at least the scattering must not be so complicated to describe, because we can always have the approximation of Rayleigh scattering to model it in such structures. So thank you for your attention.
Thank you very much. It's an interesting talk, and we have time for questions, 1 or 2.
Thank you for your talk. I have one very simple and maybe kind of stupid question, but I just ask you. So actually, you are growing artificially your ices that you study, but you talk about the ices that are the interstellar ices or somewhere in the space, yes? And how do you estimate the difference in the parameters of these ices? I mean, artificially structured that you used, and the interstellar ices.
It is a good question, but it's not so distantly asked for me, because I am not a chemist and I'm not the astrophysics. But in my opinion, and as far as I know, the ices in space are approximately the same, with at least one big difference. They are much smaller in thickness. So what we study here, and we study quite thick ices, as you can see, for example, so yeah, here you can see the thicknesses, the total thicknesses of the ices, and we need to study thick ices because we study it at the Terahertz region. But if we will move to the bulk dielectric properties with accounting of scattering approximately, then these dielectric properties will be much closer, in our opinion, to the dielectric properties of the ices in space. And one additional one addition that ISS in space, why there are so much interest to targets and far infrared region now. Because when you study ISS in the infrared region, you need some background light sources. When you study ISS in the targets and far infrared, they are emitting radiation itself. So you can study much more objects in space.
Thank you.
Thank you very much for your talk, and we finished this section. We have several little minutes for coffee break before next section.
Dear colleagues, let's start our last session, last but not the least. And the first talk will be delivered by Dr. Vasily Gerasimov, Terahertz surface plasmon refractometry of conducting surfaces and thin dielectric lasers in the Novosibirsk free electron laser.
Thank you for my presentation. Today I will present the experimental techniques of surface plasmon refractometry, which elaborated in combined with Scientific and Technological Center of Unique Instrumentation in Moscow. The first motivation, in different areas of photonics, especially in terahertz region, it is important to know optical constants of transition layer on metal surface, very thin graphene layers, like also biological samples, photonic crystals. The thickness of these layers about from 1 to several hundred nanometers, which is 3, 4, or 5 orders less than the wavelengths in terahertz region. If we use a conventional technique by reflected or transmitted wave of freehanding layers or layers deposited on the conducting surface, we have a lack of the sensitivity, and we need to use other techniques, more sensitive techniques, such as terahertz ellipsometry, metasurfaces, and also I will present two refractometry techniques used surface plasmon polaritons. Surface plasmon polaritons is the electromagnetic excitations propagated along the conductor and dielectric interface combined with oscillations of electrons on the metal surface. To excite the surface waves, we have a momentum matching between surface plasmon polaritons and external waves. The surface plasmon can excite on conductors with negative part of real negative part of dielectric permittivity, which have noble metals, doped semiconductors, dielectrics in absorption lines, and graphene and metasurface. And also it's important to know properties of surface plasmons, because today it's very intensive developed different kinds of plasmonic components used in integrated circuits in terahertz region, like in terahertz wireless communication systems. And it is a long-standing problem in terahertz region to measure exactly optical properties of metals. In the case of conventional time domain spectroscopy in transmission or refractive geometry, we obtained high value of dielectric conductivity, which agree well with permittivity of bulk metal crystal. And in the case of surface plasmons, we obtained 2 order less dielectric permittivity. It's very big discrepancy, and the qualitative explanation of this phenomena is based on interaction of incident wave with metal. In the case of conventional technique in reflection on transmission geometry, the most part of the incident wave interact with bulk metal crystal, and the little part with surface inhomogeneity. It is a typical image of metal surface deposited on the substrate, is granular structure. In the case of surface plasmons, electromagnetic wave propagate into the metal only in skin depth, and which comparable with size of this granular structure. And we need a plasmonic refractometry technique to measure the optical constant of surfaces. And before I will present the
our reflectometer techniques, I say a few words about backgrounds in Terahertz plasmonics in our which elaborated our lab, and we can excite surface plasmon polaritongs by simple end-fire coupling technique with efficiency up to 60%. The propagation length of surface plasmons is up to 10 or 1000 millimeters. We can reflect surface plasmon by metal mirrors and divided them by dielectric splitters. We also can separate surface plasmons from strong parasitic bulk waves, which introduce in plasmonic schemes, and surface plasmons can jump through microscope air gaps. And we conduct our experiments on the Novosibirsk electron laser facility, which is located in Novosibirsk. Is a big accelerator, 40 meters, which consists of accelerator, undulator with recuperation of energy. And nowadays we have 3 NovaFel, which generate 100 picosecond pulses with repetition rate 5.6 megahertz, and the quasi-monochromatic radiation of NovaFel can be tuned in the frequency region from 0.7 to 38 terahertz. And the first experimental setup is a Michelson interferometer based on surface plasmon polaritons, which propagate on the sample, and is a classical interferometer, and the detector detects the interferogram of surface plasmons which interfere, and by analyzing plasmon interferogram we can obtain real and imaginary part of refracting index of surface plasmons and of course phase velocity. And this is whole setup of this interferometer, which consists not only plasmonic interferometer, also bulk wave interferometer, which need to control wavelengths of radiation generated by Novosibirsk electron laser. And as a samples we use glass substrate covered by gold layers, and optionally covered by zinc sulfide coatings, which have thickness varied in from 0 to 3 microns. This is experimental results for metal dielectric permittivity, effective metal dielectric permittivity measurement of surfaces, which we conduct with samples with different thickness, and we need to use thickness enough high, larger than 1 micron, to make exact nice pressure, high, nice pressure, good. To obtain good results, we need to use these coatings, and the value of dielectric permittivity is here that less than the Deruda model predicted, about 1 order, and higher on order by, which we obtained by plasmonic reflectometry obtained with uncoated gold. The reason for the last discrepancy is in radiative losses of surface plasmon polaritons. When surface plasmon propagate along metal surface, it interact with imperfections, optical imperfections, and can be irradiated into free space. And when we use coatings, we can significantly suppress these radiative losses. And we have two process of losses and Joule losses, which increased with thickness of coatings, and radiative losses, which fast decrease with thickness of dielectric coatings. And in the case of an uncoated metal, we have about 4 times larger radiative losses than Joule losses. And this is experimental results for propagation length of surface plasmon polaritons obtained for different dielectric coatings and for different wavelengths. You can see maximum of propagation length at certain thicknesses. It obtained from radiative losses minima, so you have maximum propagation length, and the optimal thickness is increased with increasing the wavelength is a phenomenological dependence. Let's see the dependence obtained for wavelengths from 141 microns. It has a maximum, and green line is a Drude model. It's a long-standing problem to understand why this discrepancy exists, but in the case of small thickness, we have radiative losses, of course, and in the case of thickness larger, the radiative losses is negligible. Why we have so pronounced discrepancy? And we take Brueggemann effective medium model for metal surface, which contain two media, metal and air, with dielectric permittivities. This model works well in the case of nearly equal filling factors, and we can obtain effective permittivity from this equation, where L is a depolarization factor. We analyzed our samples, metal samples, and obtain filling factor 0.5 and the depolarization factor 0.3. And we calculate the blue line calculated curve when we take into account this modification, and we have good correlation, but not enough. And then let's see the granula on metal surface as put in electromagnetic wave of surface wave, and usually free path of electrons in metal is comparable with skin depth or size of this granule. In such case, electron can reflect from the boundaries of the grain and before he interact with other electrons or gratings. In such case, the collision frequency of electrons, effective collision frequency, can be increased. That used in Drude model, and we found effective collision frequency which larger than for bulk metal crystal, and we have a good correlation with experiment. And next application of plasmodic interferometry is a study very thin layers located on the sample. We put the sample on one of the arm of the interferometer, and we have shifting in the interferogram, and by using simple formula we can obtain real and imaginary part of refractive index of surface plasmons. This is the first experimental results obtained for polypropylene film with the thickness of 20 microns. You can see a good difference between uncoated sample and with polypropylene, and these 2 points obtained for graphite with the thickness of 100 nanometers. We see a good difference between for low conductance graphene and high conductance graphene. The next way to study surface plasmon characteristics is the study of the evanescent fields of surface plasmons. For such purpose, we use screening methods for measuring the decay length of surface plasmon in air. This is surface plasmon profile, and we measure samples with different dielectric coatings and have good correlation with effective medium model, which I presented before. And the advantage of this method is a non-destructive method and non-contact, which is important maybe, for example, for measuring monolayer graphene on the substrate. And next, the last technique of surface plasmon refractometry is based on exciting surface plasmons, not on metal but on semiconductors. Several semiconductors have a plasma frequency in terahertz region, like indium antimonide, undoped indium antimonide, and if we take radiation frequency of external wave close to the plasma frequency, we can excite surface plasmons, very slow surface plasmons, and having high field confinement, which is important for study thin layers on the substrate. And we take indium antimonide sample, pure indium antimonide from Institute of Crystallography in Moscow, and we, by Fourier spectrometer, we obtained optical constants, plasma frequency and collision frequency, and lattice used in Drude-Lorentz model. And to generate surface plasmon on indium antimonide, we use conventional attenuated total reflection technique in auto configuration, and by scanning gap between indium antimonide and prism, we obtain minimum in the reflection coefficient, and also we have the same minimum in angular scanning. And this is experimental scheme which we used for measuring these resonances. We have at certain gaps between prism and substrate. We have about the total energy of incident wave can be transformed into the surface waves. It's very good results, and if we put on the substrate sample layer, the resonance can be shifted, and by analyzing these curves by matrix formalism based on Fresnel formulas, we can obtain optical contents of this sample layer. And for the object of the understudy for this technique, we take quasi-graphene composite layers which produced from graphene flakes, which produced in Plasma Institute of Semiconductor Physics in Novosibirsk. And this character size of these particles about 100 nanometers. And by applying two-dimensional printing on the substrate, we can obtain very perfect layers, which is promising for flexible electronics. And the DC conductivity of such layers is an order of conductivity for monolayer graphene layers. And this first experimental results obtained for quasi-graphene layer with thickness of 35 nanometers, which was deposited on the indium antimonide. The red line is a plasmon resonance for clear antimonide, and the blue line is a resonance curve obtained for graphene. And we obtained dielectric permittivity of these layers, which is comparable with theoretical estimations by Drude model. And in future, we plan to make a parametric experimental study of such layers with different thicknesses, and want to obtain analytical model for the conductivity of such complex composite graphene layers. And in the case of applications, these graphene layers is very promising for development of plasmonic components for Terahertz integrated circuits. And the last slide is a demonstration of first time of wide field surface plasmon resonance microscopy. You can see antimonide indium substrate, which covered half of it covered by graphene layers, and in the resonance condition in certain gaps we have image. We can divide it two areas with graphene and without of them. And this is a summary of my talk, and I will want to finish my talk with we are welcome to collaboration to our Novosibirsk filter laser facility. This is a different organization which performs the experiments in our facility. Thank you for attention.
Your questions, please.
What What are the requirements for the semiconductor to can be analyzed by your techniques?
The wavelength, the frequency of radiation must be close to plasma frequency, and we can tune this frequency by doping of semiconductors, for example.
Thank you.
Some questions?
Thank you for your talk. I have one simple question. Maybe I missed it. What is the spatial resolution of your microscopy measurements?
The spatial resolution can be an order of wavelengths because we have diffraction limit from reflected radiation from the sample. But the spatial resolution in the transverse direction is very low. It's about several nanometers can be, because we can measure these resonance images in different incident angles, and by calculation we can reconstruct gradient of refractive index of such layers.
Thank you.
Can I have question from internet?
You can begin. Our room is not so large.
Извините, а можно по-русски задам? Просто вот по поводу вот тонкого слоя металла, вот вы показывали там модель Бруггемана. Получается, у вас очень такая пленка металла, там 100 нанометров, ну, условно, толщиной, и очень-очень пористая, пористость 50%. Это у меня глупый вопрос, наверное. Вот это всегда так с пленками бывает? Или можно сделать лучше? Ну, то есть, получается, поверхностный тонкий слой металла, он всегда будет пористый, с более сильным поглощением, чем обычный. Ага, то есть всегда так. И всегда у этого слоя тонкого будет больше значительно, чем у балк металла.
Thank you. We have questions from internet. Let's see.
Thank you very much. My question is the following. So far, I believed that permittivity of metal in terahertz frequency is dominated by losses. And as a result, permittivity is purely imaginary. So how we can talk about plasmon frequency, polaritons in this case? For me, just a xenic wave on the impedance surface. So maybe I didn't catch the point here. Can you comment?
Could you repeat your main questions? I don't understand. Maybe in Russian.
In Russian. Хорошо. До сих пор я всегда верил, что проводимость металла — это действительная величина в терагерцовом диапазоне. Значит, диэлектрическая проницаемость мнимая. То есть ни о каких отрицательных действительных частях диэлектрической проницаемости, о плазмонах, о поляритонах до сих пор я не знаю, кто бы говорил. Для меня это новое. Поэтому это как раз скорее волна ценника, волна на импедансной плоскости. Вот, поэтому, если вы можете пояснить, откуда берется отрицательная часть, даже для золота, для серебра, это чисто проводимость как на постоянном токе фактически. Если Джонсон и Кристи, вы посмотрите статью, там так будет. Поэтому вот, хотел бы понять этот вопрос.
Ну, если я правильно понял, почему диэлектрическая проницаемость вот этих поверхностей металлических отрицательную часть имеет, да? Вот реальная часть.
Почему вы так считаете?
Почему я так считаю? Ну,
почему она отрицательная?
Я никогда не задавался таким вопросом, потому что это, мне кажется, уже много лет известно, и во многих статьях, классических статьях об этом пишут. То есть вот вы показывали в своем докладе волны ценник, фано-моды, которые как раз на металлах, и там вот отрицательная диэлектрическая проницаемость должна быть. Это необходимое условие существования поверхностных электромагнитных волн фано-мод.
волнами импедансной плоскости, в том числе ценника, не требует это условие. Плазмоны в металлах, да, в оптическом диапазоне, где есть плазменная частота, где отрицательная действительная часть проводимости. Ну, в общем, посмотрите, вот это просто мое замечание, ну, вопрос скорее.
Хорошо, спасибо.
Спасибо.
Ну, мне кажется, что если есть большая мнимая часть, это не отменяет действительной части диэлектрической проницаемости. Почему, Вячеслав Михайлович, это
Да, для меня это удивительно, на самом деле, тоже вопрос.
Ну, есть о чем.
Нет, ну, может быть, и сейчас и не стоит развивать эту дискуссию, но может, надо подумать, да.
Хорошо, спасибо вам.
Спасибо. Maybe some questions or remarks from you? Not? So thank you, very interesting.
Thank you.
Now our second talk. Not be afraid that we are not in time, since the third talk will not be delivered. So we have time for discussion and so on. So now Dr. Mikhail Kosabokov will tell us about hierarchical multi-scale coupled periodical photonic and plasmonic nanopatterns inscribed by femtosecond laser pulses in lithium niobate.
This work has been done in collaboration with Eurofederal University, with Lebedev Institute of Physics, Russian Academy of Science, and I will talk about hierarchical periodical patterns in lithium niobate inscribed by femtosecond laser, and some words about ferroelectric domains interaction with ferroelectric nature of the lithium niobate. Flexible ultra-short pulse laser nanopatterning of bulk dielectrics appears as a key enabling technology for next generation of all dielectric material platform made of multiple stacks of different functional metasurfaces. Many applications you can see on the slide, and most of them has been demonstrated on this conference. Here you can see the examples of surface ablations, comparison between second laser ablation and femtosecond laser ablation. Due to the fast heating, we have higher gradients, prevalent ionic ionization processes, and in the result, for femtosecond laser ablation, we have much more better quality of edges. But in this talk, I will talk about action in the depths of the electric media. It's possible due to the multi-photon absorption. We can achieve it in extremely high power density of laser radiation. For example, we can compress the pulse in the time and achieve femtosecond laser pulses. That's the reason why it's popular for such applications. And second thing is tightly focusing. It requires concentrate the energy in the depths. Localize the interaction in the depths of the sample. On the plot, you can see the comparison of the distribution pulse profile, energy, and 2 and 3 photon absorption areas. Here are the examples of 2-photon polymerization technique, creating of the 3D photonic grating. And the most interesting for this talk applications is inscription of the damage tracks in the bulk of lithium niobate to create the bulk waveguide. In addition here creating the periodic domain structure for second frequency generation. It's an example of an integrated device in the bulk of the crystal. Lithium niobate, due to the combination of unique characteristics, it is widely used in electro-optical, nonlinear optical, piezoelectric, and ferroelectric applications. And we can control this set of unique properties via creating of the domain structures. It's domain engineering. And why we study lithium niobate? Every time we start our study, new effects, studying of new effects in ferroelectrics from lithium niobate crystal. It's an absolutely model material. And there are two reasons for it. The first one, it is simple crystal symmetry. Here we have only one polar axis, so we have domains with opposite signs of polarization. It's a simple domain structure. It's simple to visualize. It's simple to analyze. And the second reason why we used lithium niobate as a model crystal, it's a good enough quality of the crystal, independent of the sample on the crystal plate, or even manufactured Japan, USA, or China. All the plates have the same properties. It's very important to not only for applications, but for studying too. This is why we can study the features of the lithium niobate and transfer our results in other materials and study their unique features. Our samples, it's a congruent lithium niobate, Z-cut plates of 1 millimeter thickness. It's a single crystal axis, of course, single crystal. Laser irradiation by laser workstation with 1030 nanometers wavelengths and 300 femtoseconds pulse duration. Irradiation via scanning, as you can see on the scheme. And first of all, we study filamentation processes. On the back figure, you can see the side view of filaments. They are elongate directly to this laser source with increasing of power due to the care focusing. And we calculate via comparison the power-dependent filament lengths and relay lengths, the threshold power for filamentation. And interesting point here that when laser polarization along the polar direction in the crystal, we have higher threshold field and other the same. We use two types of techniques for analyzing our results. The first one, before cutting the sample, it's confocal second harmonic generation microscopy. This technique requires visualize our structures in the depths without damage of the crystal. But here we have contrast only domain walls. Only domain walls we can visualize by these techniques, but in the volume. The second technique, it's a high resolution technique after cutting the sample, as you can see on the scheme, and polishing, optical polishing. We scan it by atomic force microscopy to visualize topography, and piezo force microscopy technique for visualize domain structure. Because domains with opposite signs have the opposite piezo response, mechanical piezo response, and using the scanning probe microscopy, we can visualize distribution of piezo response. Here you can see the topography after irradiation. There is the set interesting thing. It's the presence of the transverse and longitudinal periods, and the periods increase with increasing pulse energy. You can see on their plot, their figure. And at the same time, the value of period almost constant with versus pulse energy. And the values you can see on the left side, 400 nanometers for longitudinal periods and 160 nanometers for transverse periods. It's deeply subwave periods, but there are differences between experimental periods and expected periods if we calculate it as lambda divided to n. That's difference we can associate it with electron plasma presence in focusing region. Here are some estimations of the electric permittivity by this formula. And we calculate, using the electric permittivity, the wave vector, and compare with experimental obtained periods. We estimate the plasma parameters we can get as such periods. The main idea here that presence of the plasma can change the electric permittivity and respected refractive index, and our standing wave, which produce such structures, can change the period in both sides, dependent on the plasma parameters. This is a scheme of idea. We have plasma, focal plasma. Due to the plasma conductivity change and changing relative permittivity, plasma reflects some energy of the laser pulse. We have standing wave in reflected area. In antinodes of standing wave, we have plasma sheets, new plasma sheets. It's a process like a step-by-step. The one part of this optical structure produce the other other part of the structure. So that's the reason why such structures called hierarchical. In each plasma sheet, we can produce plasmon polyton wave, and this is the reason of the very complicated interference pattern which produce our structures. What about the main structures? We studied it by confocal second generation microscopy. As you can see, the green contrast, green light respected to the presence of the domain walls. Everywhere where we have the defect tracks, we have the domains. And here, the study with high resolution microscopy. For each area, for each pulse energy, we have two figures. The first one is a simple topography. The second one is a PFM amplitude distribution. And we confidently state the presence of the domains in areas where, for example, here, where there are no damages. Because the each damage have contrast in the PFM amplitude. Very important point here, it's direct growth of the domains from the damages. Because usual growth of the domains usually from the surface. Surface is a big defect of the crystal. The threshold field for domain nucleation lower, and due to the conductivity of the surface, the domain is stable. We have screening of the depolarization fields, but it's for crystals with high threshold values, for example, lithium niobate, congruent lithium niobate, the threshold value for domain switching is about 23 kilovolts millimeter. So it's impossible to create just domains in the bulk. But here we create the surfaces, little surfaces in the depths, which became the centers of nucleation for domain switchings. And the thickness of the domains here equal the thickness of the damages. Another interesting thing for high energies, PFM contrast fully localized on the damages. It's difficult to analyze maybe domains between damage points presence. But domains don't grow outside the damage areas. So my brief conclusions. My conclusion is we demonstrate hierarchical nanopatterning by two-shot laser pulses. It's at the first time we demonstrate the principle of domain switching in the depths. Domain grows from the damages points only. We separate the domains and defects, damages, damage tracks. So that's all. Thank you for your attention.
Your questions, please. May I ask you, very interesting talk and the interesting book. Do you take into account photorefractive effects when this crystal has a lot of defects? It's not a stoichiometry crystal, yes? There are lithium vacancies, and small polarons are formed when you obtain free electrons after absorption. Do you take it into account that electrons are not in the free, are not free, they are localized at the vacancies?
If I understood you,
Photorefractive
I've
damage.
missed one figures, polarimetric microscopic image of damage tracks. No?
Polarons are electron phonon interactions, and the small radius polarons here are known in such crystals to be formed after laser irradiation. It is the photorefractive effect, and due to this effect we use magnesium doping of such crystals to protect the crystal from this.
It's difficult to analyze because after irradiation, after local heating, after relaxation plasma, we have freezing piezoelectric field, and field so high and change. It's difficult to analyze.
So your
Change the refractive index.
So your pure effect is enough to explain all the effects, yes?
Domain growth, of course.
Mm-hmm.
Piezoelectric super high field.
How stable are these domains after you finish your irradiation?
Some structures we studied after 4 or 6 months and didn't change the shape. We studied it by piezo force microscopy with super high resolution, and didn't change the properties. They're switchable absolutely. So it's absolutely stable for many years.
At room temperatures?
At room temperature and at higher temperatures, above up to 150 Celsius degrees.
Yes, at 150, all photorefractive damage can be annulled.
No. Ionic conductivity starts prevalent at higher temperatures, about 200 Celsius degrees, and screening field, just screening field. And if we have quasi-stable domains which don't screen, they can switch back in the lithium niobate. Only in the lithium niobate, congruent lithium niobate. In other material, for example, magni-doped lithium niobate, they have another parameters and another behavior of domain structure.
And you didn't try these crystals in such a system?
We tried. We have poster there. There in Magni OLN, the domains grows much longer up to surface from the center of the plate, about.
So such kind of laser writing is possible in these crystals also. Magnesium doesn't prevent from this formation of such laser writing of domains.
Yes, but
then you're right. Photorefractive effects are not important in this case. I see. Maybe other questions? Yes.
Thank you for your talk. I have a question. After laser irradiation, can you switch the polarization of your lithium niobate, of your material? Can you switch the
polarization?
Yeah.
Oh, here, this is domains.
Yes.
Where there are no damages. This is pure domains with switched polarization.
But you have the amplitude, not the phase. The phase will show you the polarization. The amplitude will not show you, right? Here I say is amplitude.
Amplitude of PFM signal, do you mean?
Yes.
Oh, it's so narrow. You can't resolve domain walls here. It's the main.
The direction of polarization. Can you switch it?
Polarization here of the crystal. Polarization inside the domains in the opposite direction.
How do you know? Here I see the amplitude, not the phase.
We have amplitude. I don't show you here.
Okay, thank you.
Yes, of course. Phase and amplitude, we analyze it. But it's difficult here because it's quite narrow. For pure analyze, you should resolve the domain walls, yeah? Yes. Where amplitude is 0. But if domain size about the contact area of the tip, conductivity tip of the SPM microscopy, you can't resolve it. But it's switchable structure. We can switch it, and it's absolutely proof that it's domains, predicted domains. It's switchable. We tried it.
How did you switch it? By external field?
Application of the local field by conductive tip.
So it's direct method. Other questions? If not, let's thank the speaker again. And we will turn to the fourth talk. Maria Budanova, Dr. Maria Budanova, are you here? Yes, a little bit. So earlier than it is according to this, but we'll listen. Not wait other people. Yes, maybe come directly to your talk.
Yeah, thank you very much. So organizers made a mistake in this program, and they added some co-authors, which are actually not from my research. So I would like to introduce myself again. So my talk will be about ultrafast spectroscopy of one-dimensional nanomaterials and their applications. And I came from Moscow Institute of Physics and Technology, and also I'm working in Prokhorov General Physics Institute of Russian Academy of Science. What I will talk about today is the spectroscopy of nanomaterials and why it's important. From my point of view, I think that understanding of fundamental properties of nanomaterials is incredibly important in developing of different applications, especially optoelectronic applications. So let's start. For many years, I'm inspired to stay in science because of one structure that I would like to present you today. I think you more or less know Graphene Guy's game and Novoselov, who won a Nobel Prize. And as you know, that as the next step of their research, they decided to build heterostructures based on very well-known 2D materials, trying to develop new properties. In the similar way, a couple of years ago, my collaborators from Japan University, they decided to make so-called 1D van der Waals heterostructures. And at this step, they created the structure based on carbon nanotubes, boron nitride nanotubes, and MOS2 nanotubes, which are known as quasi-one-dimensional nanomaterials. And when I had those materials in my hands, I asked a couple of questions to myself. The first question was, you know that graphene, MOS2, 2D counterparts of nanotubes, they are quite very well developed, and their properties, we know their properties quite very well. So my main question was, are there any difference between 1D and 2D materials? Can we develop absolutely new property that we can use in optoelectronics? The second question is, can curvature that we have in nanotubes result in new properties? Another important question, as we have a one-dimensional material, so we should expect some localization of properties along the nanotube. Also, when you have a heterostructure, you may ask yourself a simple question, whether we have properties related to heterostructure itself, or we have properties like a sum or a combination of properties of individual components. So it's a very important question for people who are working with heterostructures. And today I would like to show you that by using ultrafast spectroscopy, you can also obtain the information about the contribution of free charges and excitons in the properties, which is also important for optoelectronic applications. So, as you know, nanomaterials, it's very hard to obtain such interesting, exotic, I would say, heterostructures. So first of all, we need to verify that we really can grow those materials. And at the left-hand side, you can see transmission electron microscopy images of carbon nanotubes covered with boron nitride nanotubes. And a little bit right, you can see that now we deposited MOS2 nanotubes and the density is changed a little bit. But anyway, electron energy loss spectroscopy that you can see at the right-hand side showed that we have kind of Russian doll structure when we have carbon nanotubes, boron nitride nanotubes, and MOS2 nanotubes. So we really have this structure on a wafer scale films that we now can investigate using different techniques and target spectroscopy as well. So let's have a look, first of all, in a broadband spectroscopy measurement that we have done for all 3 samples. Here, red line corresponds to carbon nanotubes, and as for all nanomaterials, we have here the excitonic absorption lines, even at room temperature, this is for carbon nanotubes, those absorption lines appeared in near infrared region and middle infrared region, while in terahertz region you can see the increase of the absorption, which could correspond to the plasmons and non-localized druid-like response in this material. So as a next step, as I told you, we covered carbon nanotubes, which are metallic and semiconducting in nature, with a dielectric insulator, boron nitride nanotubes. What happened here? So as you can see, in the whole range, there is no difference except 2 parts in UV region. We have a strong absorption line from boron nitride nanotubes themselves, because it's an insulator, so it's around 6 electron volts. And in middle infrared, it's middle infrared region, we have vibrational modes. It's infrared active modes from boron nitride nanotubes themselves. And those modes are different from bulk material, as you can see on inside. And as the next step, we deposited MOS2 nanotubes, and here you can see that the spectra changed, and now we added some absorption, excitonic absorption features in visible range. So now we have absorption lines in visible range and some absorption from MOS2 nanotubes and some absorption lines from carbon nanotubes in infrared region. So if we look if we compare the results with 2D materials, we can see the shift of those lines, which told us that the curvature and a lower dimensionality of this material result in significantly different optical properties. And here I just visualized the vibrational modes of boron nitride nanotubes, which are actually, they are infrared active and also Raman active modes. So let's now move to Raman spectroscopy measurements, and for carbon nanotubes it's very well known that they have so-called radial briefing modes when carbon nanotubes carbon atoms are moving in radial direction. So it's a very useful technique to obtain the diameters of nanotubes. But for my own research, what I obtained from Raman spectroscopy measurement, at the top you can see at lower frequencies, you can see carbon nanotubes response, it's a red line. And when we deposited each of the layers of boron nitride nanotubes and MOS2 nanotubes, we observed the shift of the frequencies, and also we observed the decrease of the intensity for those vibrational modes. So this is the indication of the damping effect, which came from each of the additional layer that we deposited. Also, we compared for MOS2 nanotubes, we observed in-plane and out-of-plane vibrational modes that you can see at the bottom part at the left-hand side. Those modes become different from bulk material or even from, in comparison to monolayer material. So this is the middle part. So we really proved that we created 1D material which show different properties, optical properties in comparison to 2D material. Let's now move to terahertz spectroscopy. So, as I told you, we observed an increased absorption towards higher wavelengths, also lower frequency, and here you can see the real part of the conductivity multiplied by the thickness. For carbon nanotubes, this is red line, and here there is a contribution from Drude response and also from plasmons. And when we deposited boron nitride nanotubes, we somehow decreased the conductivity, which could be attributed to the introduction of the additional insulator layer between carbon nanotubes, which reduced their conductivity. And when we deposited MOS2 nanotubes, we somehow increased again the conductivity, which could be attributed to the jump of the free charges between carbon nanotubes and MOS2 nanotubes, so between different parts of the heterostructure. Also, it could be attributed to the tunneling effect. You know that boron nitride nanotubes, they are insulating in nature, but there is still, the charges have still an opportunity to jump between carbon nanotubes and MOS2 nanotubes, even in the presence of such high potential barrier. In addition, MOS2 nanotubes themselves, they can exhibit, they are semiconducting in nature, but when we are growing them, we usually have a certain amount of defect that can result in additional conductivity as well. So, and my favorite method that I used is optical pump terahertz probe spectroscopy. It allowed us to measure a photoconductivity of such materials, and here we actually this technique requires the knowledge about the absorption in visible range and also in terahertz region. So what we did here, so we performed terahertz spectroscopy measurement, and we additionally excited our sample with a femtosecond laser, varying the time arrival between those two pulses. And at the left-hand side, on the top, you can see the relative change of the amplitude of the transmission function as a function of time for free samples, and red curve is for carbon nanotubes, and boron nitride didn't change the dynamics at all. But when we deposited MOS2 nanotubes at certain wavelength that we used for photo excitation, we observed the change of the sign. You can see it on green line. So, and after that, at the bottom, we varied the photo excitation wavelengths, and when we excited our sample above with the wavelengths or energy above the band gap of MOS2 nanotubes, we observed the change of the sign, while when we excited it below gap, we didn't observe this change of the sign. So it's a clear signature of MOS2 nanotubes. And we obtained we attributed the conductivity, photoconductivity for carbon nanotubes to the formation of trions, charged excitons, and for MOS2 we attributed to presence of free charges. So as the next step, we performed optical pump, optical probe measurement. So it's so what we are measuring here, in the similar way as I showed you at the beginning, we measured the absorbance, but in additionally again we excited our sample with a femtosecond laser, varying again the time when the one pulse is arrived relative to another one. So, and here you can see the map that we obtained. So there is a photo-induced change of the absorbance as a function of time. And I don't want to talk about it too much. I would like to move to the applications. But what I would like to show you here is that there are some areas, blue areas. And if you look at the position of those blue areas, which corresponds to the photo-induced transmission, those lines quite very well aligned to the absorption lines that we saw at the beginning. So those features those dynamics are definitely from excitons, and so I would like to show you that both OPTP and optical pump, optical probe measurements allowed us to measure excitons and free charges, which are together present in our material. So, and the knowledge, this fundamental knowledge about this material allowed us to construct several very interesting devices. Some of them are quite simple. The first one is optically controlled terahertz modulator. And for modulators, as you know, there are two parameters which are important. This is the modulation depth, which showed us how much we change the sign when we are or how much we change the signal when we modulated it, and the modulation speed characterize how fast you can operate with this device. So here I plotted a modulation depth for different material, for different thickness of carbon nanotubes. And carbon nanotubes are quite they are very good optically controlled modulators. And what we obtained here, that the modulation depth is about 80%. And the modulation speed is about 300 gigahertz. You can see that there is an impressive time scale, so the signal when we excited the sample, it recovered to the equilibrium state within, let's say, 15 picoseconds, so it's quite impressive. And we compare this result with very well-known modulators, and really we can use carbon nanotubes as terahertz modulators. And one of my students, he investigated the effect of stretching to the performance of such modulators. And what he observed, that there is, he stretched it and then he relaxed the films, carbon nanotube films on elastomer. And what he observed, that there is a deterioration of both modulation depth and modulation speed when we stretched our modulator. But there is a good point that by stretching we can tune both modulation depth and modulation speed, and we can set the certain parameters for certain applications. There are two more applications that we have discovered by using those nanotubes. This is tunable terahertz Fresnel zone plate. The idea is very simple. Nanomaterials, they have a benefit in comparison to solid-state materials. We can stretch nanomaterials without the deterioration of their properties. And here you can see that our collaborators, they made such zone plate for us, and we stretched it, and according to the simple formula that we know even from the school, by stretching, by changing the geometry, by changing the ring size, we can control the focusing position. So, and it's quite very well working in terahertz region around 300 gigahertz. And here I just showed you that under 20% of relative change of the radius, we observed the shift of the focus position of such a lens up to 10 millimeters. And there is one more work that we are doing at the moment. This is my students' work as well. The similar group, they made spiral zone plate for us, and as the next step we decided to control the performance of our optical element, but by putting one element on the top of another element. So we used two spiral zone plates, and we looked what the combination of them will give us. So at the top you can see how the intensity of the terahertz beam at certain frequency is changing when we have two spiral zone plates that we are rotating at certain angles. And what you can see here, so we can see a couple of different scenarios. We can see ring, we can see two beams, we can see four beams, so it's just in one So this is the vortexes. And how we can use it, so by simply rotating one spiral zone plate relative to another one, we can split beams into 2 or 3 beams, which are important for many applications such as multiplexing and demultiplexing. But this work is in preparation. And finally, I would like to show you one new setup that we have developed in Institute of General Physics in Moscow. So this is optical pump terahertz probe spectroscopy setup. And now we can tune the wavelengths for our setup from 400 nanometers up to 2.2 microns for pump excitation. And we can track the photoconductivity dynamics in the range of even a couple of nanoseconds with a quite impressive time resolution. And also, as you know, for terahertz spectroscopy, we can also record photoconductivity spectra. Right now, we have crystals which allowed us to measure it between 0.2 and 2 terahertz. So we're very welcome to measure any interesting samples on our setup. And finally, I would like to acknowledge all of those people who helped me with my work, especially my students, Maxim Paukov, who 2 days ago gave his talk as well, Vladimir Starchenko, and Arina Radivon, who is working on vortexes. And if you have any questions, I will be happy to answer them.
So I have a question about this dimensionality, about one-dimensional structure.
Yeah.
I guess that the main difference between two-dimensional and one-dimensional structures is the dimensionality of transport properties.
Yes.
Do you have any evidence of this anisotropy in transport or in electrical properties, or at least polarization resolved? Or probably splitting of exciton lines or whatever.
Unfortunately, 20 minutes are not enough to explain everything, but in my papers you can see two things, two properties that can answer your question. The first property is the formation of plasmons in terahertz region, which is a clear signature of localized charges.
But is it anisotropy? So
anisotropy, yes, we have anisotropy. I never investigated it, but usually people told me that it would be good to perform those.
You didn't see any anisotropy, but you still believe that your structures are one-dimensional.
Sorry?
So you didn't see any anisotropy in optical properties, but still believe that all the structures you study are one-dimensional.
There are quite a lot of different articles which prove that carbon nanotubes have anisotropy, but in my measurement, pump probe measurements, usually because of the developed setup, we have pump and probe perpendicular to each other, so I can't really say whether we. So in my case, the media, the properties that I obtained are more about oriented material, randomly oriented material rather than aligned. But people many times suggested just to try maybe different polarization or even align those materials, but it's quite hard for us right now.
Did you see probably any kind of splitting in exciton lines? Because if you have a nanotube,
unfortunately not. So it was the main point why people created it.
What's
yes.
the reason?
So for carbon nanotubes, we have the splitting we have singularities in valence and conducting bands, and the main reason why we wanted to make such exotic heterostructure is to obtain the same property for MOS2 nanotubes, but unfortunately we didn't observe it for some reason. I don't know, maybe someone will prove it at some point, but
Probably
for now we didn't.
If possible, the last question. Can I ask?
Maybe I have one more comment,
okay,
sorry.
go ahead.
Yes, about the dynamics itself. So I didn't tell you about it. I have also a paper about it. Optical pump, optical probe measurements allowed us to track the excitons. And when we're using very high excitation, we can observe exciton annihilation. And excitons traveling along the nanotube and crashing on another excitons, they can diffuse in one direction or in two directions. And for this particular material, we observed that we have kind of an intermediate state. We have 1D to D diffusion of excitons. So we can't fully claim that 1D MOS2 nanotubes behave like one-dimensional materials, but it's still not the same as for 2D material.
Okay, and in these materials, so the radius of exciton is quite small.
Yes.
And what's somehow the ratio between the exciton radius and diameter of your nanotubes?
Yes, that's a good question. For carbon yes, this is the idea which came from carbon nanotubes. Their Bohr radius is significantly bigger than their diameters. Therefore, excitons are more localized along carbon nanotubes. But if we look at the transmission electron microscopy images of our heterostructures, we can see that the diameters are something like 15 nanometers, and the Bohr radius that we calculated for MOS2 nanotubes, they are around 1 nanometer. So it's like an Earth, right? So the curvature is not enough to produce the localization effects. So this is my question. So you can see here that the diameter is around 15 nanometers. So it's quite big. But this is what inspired us to investigate the sample.
I have a question about your mechanical stretching zone plates. What about mechanical memory of these plates? Can they used for modulation of beams? Mechanical stretching. When you stretch your plates.
I probably understood your question, and I think it's more relevant to the degradation of our sample as well, right?
No, I mean when you move your focus after stretching, the focus return to the initial position. Or,
I got it. We used to avoid any problems. It's kind of reversibility, right? For thin films, there is a degradation of our element because we started to observe micro cracks, which didn't allow us to move back to the property that we had initially. But if you are using very thick carbon nanotube films, we can avoid it. That's what I don't know whether it's so, but that's what we observed.
And the next question about your diffractive optical elements, you make it from carbon nanotubes?
Yes, carbon nanotubes. Yeah.
Okay, thank you.
Yeah.
Any questions else?
Thank you for your talk. My question is about the level of your electric fields for terahertz and for optical field. How do you prove that the terahertz in optical pump terahertz probe, that your terahertz probe does not change anything in the material? How do you prove it? Because in your analysis there are no words about this. But it's really very fundamental thing for any pump probe experiments.
Yeah. So in my work, I used different setups from different groups, and honestly, I started my research in England in James Lloyd Hughes laboratory, and then I moved to Russia, and now I'm investigating those samples in General Institute of Physics, when I was in England, we used such emitters like spintronic emitters, and their intensity is not too much to obtain some nonlinear effects. But right now, yes, we're using lithium niobate crystals, but we also check the power. And I think maybe it's a little bit stupid, but I would say that a couple of groups published the same results in the similar time, and we observe the same effect. And also, I know what to expect from high field measurements. I a little bit performed it, and I know what to expect. No, we didn't observe such effects here.
Maybe some missed in your presentation. So you see no damage after no incubation effects when you just shine your sample. You just not shifted it along the excitation. Yes, am I right?
Yeah, I understood your question. So it's very easy to track it if you are damaging your samples. There is a deterioration of your properties, which you can immediately see. So in my case, for example, if I apply too much more power from pump, the photoconductivity will reduce immediately, and I can track it. Here, for example, you can see I didn't use the fluence more than 210 microjoules per centimeter squared, so it's enough to observe some effects, but we didn't damage our sample as such fluence.
But I think that not the energy density, but the intensity is more interesting for my question. Here you can see the microjoule per square centimeter is the energy density, not the intensity.
Fluence.
Okay,
Yes,
okay.
fluence.
Fluence.
But what I would say, I avoided the power that damaged my sample because I saw it by eye how the photoconductivity is deteriorating under the high power. So I avoided it.
Okay, thank you.
I think not direct damaging is important. You use your terahertz. You spoke about the terahertz pump also experiment.
No, optical pump, terahertz probe only.
That
Yeah.
Terahertz pump.
No, not yet.
Not yet.
Hopefully in the future.
Thanks. What are the questions else? So thank you very much for your talk. And many thanks to all of you who come to this last session and for your attention. And the session is over.
It's over.
He wasn't before. So the session is not over. Sorry very much. So Fan Xiangui, yes, and the title of the talk is Velocity Overshoot and Terahertz Generation in Aluminium Gallium Arsenide Structured PIN diodes. Please speak.
Thank you. Good day, everyone. Thanks for the chance to present my report. The topic of my present is velocity overshoot and terahertz generation in aluminum gallium arsenide heterostructure PIN diodes. Compact and inexpensive time reward terahertz spectrometer beside an optical terahertz photoconductor transduction of untranslated laser pods are activity development and found wide application is low fundamental and applied problems. To a large extent, the high activity of research in this direction is associated with the improvement of the terahertz spectrometer, which is determined by the improvement of the detector and emitter parameters as a terahertz emitter, photoconductor, semiconductor antenna, and bulk indium arsenide semiconductor are mainly used. Semiconductor layers of A3B5 conductor grow by molecularly become impacted and at a reduced temperature are used as a photoconductor in PCs. Future improvement of terahertz emitter is associated with the use of structure based on metal shafts and PIN diodes. So this is my outline for the report. The first work of the study of terahertz generation in silicon PN was done in Austin. Besides all the previous experience and data, this paper presents the result of an experimental study of terahertz radiation generation in heterostructured PN diodes and excitation by femtosecond optical pulse. I think everyone have already heard about the appeal of the terahertz band anyway. The simple understanding is shown in the figure. The bottom right figure shows the zone diagram. This cell shows other the characteristics of PN diodes, dark and light current voltage carriers, spectral photosensitivity. Titanium sapphire laser generation optical pulse with duration of 15 femtosecond and 100 femtosecond at a wavelength of 800 nanometer were used to excite the study samples. Terahertz radiation was recorded using an electro-optical gate technique in spectral refluxes. Generate result shows schematics of the experience setup. In the study of terahertz radiation excited from a PN diode, it was found that the maximum effect of terahertz generation is obvious at the application of reserve base over 8 volt, and the level of optical excited up to 10 millivolt. This is a linear dependence of the terahertz pulse amplitude on the average power is fixed. The left figure shows the dependence of the amplitude of terahertz pulse generated in the PN diodes and the Indian adjacent diodes on the average power of the optical pulse. The amplitudes of terahertz pulse were determined from the waveform of terahertz pulse then in diodes. They are shown in the right figures. Compare study of terahertz generation in the bulk semiconductor P-Indian ascendants were carried out which show that the effect of terahertz generation in the PN diodes is an order of magnitude higher than in P-Indian ascendant. The left figure shows the waveform of terahertz pulse generation in PN diodes and P-Indian arrays, and the right figure shows the spectrum of terahertz pulse. It is clear to see that the amplitude of terahertz pulse generated in PN diodes is 4 times larger than the amplitude of terahertz pulse generation in P-Indian arrays. Accordingly, the energy superiority is more than an order of magnitude. When we studied the terahertz generation process in a PN diode, it was found that the terahertz pulse waveform depended significantly on both resource base excited level and excitation quantum. The upper left graph shows the waveform of terahertz pulse generation in a PN diode and reverse decided from 0 volt to minus to 7.5 volt around the power at 8 millivolt, and the optical pulse wavelength 783 nanometer long. We can see that the maximum amplitude of the pulse increases as the result based on the time that increases and the time possible of the pulse also change. The upper right figure shows the delay of terahertz pulse generated in PN delta from base for different excited quantum. The lower right figure shows the amplitude dependence of terahertz pulse on base for the same excited quantum. On the left, the bottom left figure shows the both of this dependence. It was be seen that the maximum amplitude of the pulse grew steeply with the growth of the reverse base, while on the delta with the set of this group depending on the energy of the exciting quantum. Accordingly, the time position of the pulse also changes at a chance of while of the resource mixing on the delta, and at a chance of mixing well from positive wells up to the well of valent on the delta at with the cell growth of the pulse amplitude begins. There is delay of the terahertz pulse with further increase of resource mixing on the delta. The terahertz pulse is revealed on the time scale. The mountain current cell of terahertz process is dark. The dynamics of photoexcited electric hole problem in the study sample was made using the mountain current method. The time dynamics of the current of non-nuclear break carried in the pin that was calculated taking into account the ballistic mountain of electron with the subsequent possible set of the average value much higher than the saturation value, and their interval transition from the G value to the L value. The upper figure shows the time dependence of the current from two excited quantum. The bottom figure shows the dependence of the possible of the maximum current amplitude on the magnitude of the result based on the data. The electric field of terahertz radiation is in the far field can be defined as the difference of the current. So accordingly, the cousin of the office dependence of the terahertz pulse possible will correlate with the current of the maximum current amplitude depends. This the mountain current simulation confirm. The experience result, but most important in determining the emission of the measures of terahertz generation. Normally, terahertz generation in the PN diodes is caused by acceleration of the electron in the electric field to a velocity much higher than the saturation value of the order of hundreds of femtoseconds. The dependence of terahertz field of the average power of excited optical radiation are not a monetary function, but have a minimum. The possible of which depends on the value of the research base. AC cell field so the excited spread of terahertz generation at a high level of optical excited and at a reverse based less than 8 volts. The effect of terahertz generation drops sharply due to shielding of the applied electric field by the field caused by restriction of non-equilibrium change carry and possible also by shock ionization in narrow correlates dynamics. Also, the dependence of the terahertz field on the research based on the PN data is not a monitor factor. The reason for such non-monitor behavior at great values of the available power of the excited optical release and the value of the research based on the PN data in the presence of the internet. In the internal research of the PN data, we performed experiment with the content of additional research in the PN data power was sharply greater. The results are on the next scale. It can be seen that the content of actual result changes the positive of the minimum on the current of dependence of the terahertz port applied on the average power of the optical port. The upper figure shows the equivalent electrical current of PN diodes, which include a capacitance and internal resistance. This slide shows the waveform and spectrum of terahertz pulse generation in a PN diode are under-excited with 15 femtosecond optical pulse. The optical values of the spectrum when the 2.5 terahertz is determined by the parameters of the experimental setup rather than by the physical of the generation process. This beside on the optical the of terahertz generation in PN that is as follows at excited of the PN that structure non-equilibrated electric and hell are brought in the air region, which node in the electric field hell to P aluminium gallium arsenide electric to N gallium aluminium gallium arsenide at electric field are more than 400 watt per centimeter. Electric in millimeter at time 100 femtosecond, equated to a velocity much higher than the saturation velocity. With the subsequent interval transfer from G value to L value. As a result of the interval transition, the electron velocities drop significantly due to the change in effective mass. The initial position of the photo-excited electron determines the time of its ballistic transit and the time of its set corresponding to the velocity for the interval transition. Accordingly, we have sharp rates in current and subsequent cell for which leads to effective terahertz generation. The summary, the result induced that the mechanism of terahertz generation in PN diodes is due to the acceleration of electric in the electric field to expand significantly, exciting the saturation span at a time of hundreds of femtosecond and the suboptical cell delays associated with the interlayer translation of electric for the G vector and the scattering effect of the internal electric field by separating electric and health. The effect of the sharp drop in in Terahertz generation effect at a high excited level can be explained by the effect of electric field shaded by photo-excited electric holes and sharp elongation in narrow collisioning demand. It was shown that the generation effect in the pin does at excited levels and at which a layer dependent of the electric field applied on the optical radiation in Terce is observed in its an order of magnitude higher than the terahertz generation effect in the P in the resident block semiconductor. It is the most effective terahertz emitter. That's all. Thank you very much.
Please. Thank you. And what are the questions? May I ask you about you compare your results in generation with the P indium so in comparison with biased photoconductor structures from the same aluminum gallium arsenide and other materials, so can you compare these Terahertz abilities, generation abilities, with the photoconductive material, photoconductive antennas? The question is not clear? The answer is not clear. Maybe your colleague will answer. Not? Co-author? So did you hear the question?
In the in plasmic condensator.
So can you compare the generation efficiencies in your PIN diode with the same generation efficiencies in the well-known photoconductive antennas? So biased semiconductor structure. Do you have other questions?
I think it's the same.
The same. Thank you.
Thank you.
Thank you. So let's thank the speaker again.
Thank you very much.
And let me again to close our session. If no other points will appear, so see you at the next conference. Yes.